but that are not related to the lab itself, but other interesting things, like, for example, today we have Stefano Ossicini, that he will give us a talk about ethics in research, but we have also Professor Rodrigo Martins that will talk to us about the ERC, that I guess you already know, but he will give us some special notes about it, and also Monica Bello, that is the head of arts at CERN in the CERN. And also during this week, during the Tuesday, Wednesday, and also Thursday, you will have the welcome activities to start the day that I will talk to you later. So as Professor Obrador said, this school is in the framework of the DocFam doctoral school, doctoral program. This DocFam program is a Marie Curie co-fund project that is coordinated by ICMAB, and also ICM2, CNM, IREC, and ALBA are part of the program. And the aim of this doctoral program is to give the fellows, there are 22 fellows in this program, to give them experience in advanced functional materials and that they share it and export it internationally. For this reason, during this school, in the second part of the school, which is Wednesday to Friday, you will have the talks from the DocFam fellows that are also here today because they are also attendants of the school. So part of your colleagues in the school will give also the flash talks about what they do in their research, and so that you can have an idea of the DocFam program and what we are doing as research. And also Thursday afternoon, we have the poster session that some of you will present posters. We have 16 posters. And also to round up the school on Friday, we will have a round table with 4 professionals that did their PhD, like you are doing now. But after the PhD, they changed their professional paths, their career paths, and they are now working in different things. So the idea is that this day you can talk to them and ask them the questions. I don't know if you are thinking to change your career path after your PhD. A lot of you are in your last year, so maybe I think it's good that you can talk to them and ask them questions, what you need to do, how to prepare your CV, what kind of training do you need. I mean, it's a good opportunity to have a chat with them because it will be a very informal session, and they will be happy to answer your questions, okay? And also very important, as Professor Obrador said, this school was going to be a school to be done at ICMAB, so you can know each other and so on. But due to COVID-19, it was not possible. But we still want to have this kind of feeling that you can interact with each other, you can chat, you can know the research of your colleagues at the school. So it's it's very important. It's very important that you participate, that you take part in the school. For this reason, the talks are organized that they will speak for 40-45 minutes, and then we have put 15-20 minutes of discussion so you can talk to the speaker. So for them, it's nicer to speak to you than to speak to a screen. So I invite you to ask questions to the speakers. They are very recognized researchers, and it's your opportunity to ask them all your questions, and they see you, they meet you, and take this advantage that you have the opportunity to chat with them. So I ask you that you have your microphones and cameras ready for any time, so you can ask the questions, and you can use as you know, the reactions system to raise your hand, and we will let you speak for the questions. And also we have the welcome activities every day at the beginning of the day. During half an hour, you will be divided into little groups. So you will enter the Zoom, and instead of being in the Zoom right now, with all your colleagues, you will be divided in little groups, in breakout rooms that they are called in Zoom. And there will be one person that will introduce you to an activity, and it will be an activity so you can interact with your colleagues and know them, what they do, and these kind of things. And then after half an hour, you will be automatically directed to this main room. So you don't have to worry. You just enter the Zoom and you will be part of the activity straight away, okay? And of course, you can talk to each other through the Zoom chat. As you know, in the chat, there is an option to send direct messages to your colleagues. So you can chat anytime, you can speak to each other, no problem at all. And some of you already know each other, especially the Dog Fund Fellows, because they have been working together and so on. So I invite you to try to have the most similar experience to a normal school, even though it's online. And just to finish, and now it doesn't work. Okay. Just to let you know that on Thursday from 3:30 to 5:30, we have the poster session that it will be in presential mode. This is the only activity in which we will be able to see each other in person. It will be at ICMAB Terrace, and you will be divided into two groups because you are a lot of people and we cannot have so many people together. I will send you an email with your assignment. I think we will do 1 hour each group, more or less. The people in the posters, they will be the 2 hours in the poster session because they have to present the poster. But the others, the people that don't have poster, you will come to the poster session during 1 hour, okay? Of course, the mask is compulsory because we will be a lot of people around. So it's please use your mask even though it's outside. And please respect the distance of 1.5 meters, 2 meters, so we don't have any kind of issues. And sadly, no food will be served, although it's always nice to have a poster station with some snacks, but it's not possible. It's the security rules of ICMAB don't allow to have food, so there will be no food. And on Friday, we will give an award to the best dog fun talk and the best poster presentation. And you, the attendants, will choose who is the winner. So please take all your attention to the dog fun talks and the posters because you will have to vote for the best dog fun talk and poster. So you will decide. And that's it for my side. I don't know if you have questions. You can unmute yourselves if you have any question. It's the time because we still have 10 minutes until we start with Professor Marzán. So please, if you have questions, unmute yourself. No questions.
No, we have 51 participants, no?
Sí.
Sí. No sé si ho veuen ells, això?
Sí, sí que em veuen, sí.
Okay.
So no questions, you are very shy. That's not the way to start. Okay, I don't know if Luis is around, but still we have to wait 10 minutes. So if you need to go to the toilet or you need to take a snack or something, we'll start at 12. So because we are having a streaming, so we will start at 12 sharp. So if you want to take a rest, it's the time. If you want to, we can all switch on the camera and we take a picture of all of us for the social networks. If you don't want to, it's fine. Okay, so I think Anna will take the photo. So Anna, you can tell us once you have done it. So switch on your cameras if you want to. Artur.
Okay, it's done. Thank you.
Okay, so we have already Luis here and Agustin, who will be the chair of this session, is connecting. So Agustin, once you're ready, you can already start.
Okay. Good morning, everyone. So I go ahead and initiate the session, right? It's not noon yet.
Okay, so let's wait 2 minutes. So we have.
We wait a few minutes. Yes. Yeah. It's true that the introduction will be long because Luis has a very long CV.
And I'm probably going to speak too long anyway.
Hopefully. So we wait a few more minutes, if that's okay. Guessing for the questions, Laura, we will be maybe reading them from the chat, or if someone wants to ask a question directly, you can.
I told them that if they want, because I told them that it's nice to speak in the camera with the speaker.
Yes.
I told them to have the cameras and microphones ready, and if they want to ask a question, that they can use the reactions in the room. You know that you can raise your hand in the reaction. Yes. Or the other reactions they can use, because I think sometimes the hand doesn't appear. Mm-hmm. So the reactions to ask for the turn for the questions. And if they don't want to put the camera, they can ask in the Zoom chat also.
Yes, we will accept questions in every form.
Yes. And also we are having the YouTube streaming, and I don't know, maybe there are questions also in the YouTube streaming. So Anna, I think Anna is checking the YouTube, and she can tell you about the questions there.
Okay, excellent. Yes, we encourage everyone to ask questions. It's a great opportunity to have Luis here, and let's know more. So welcome everyone. Let's start this presentation by Professor Liz-Marzán. It is really our privilege to have him speaking today. It's also my honor to introduce him. I'll give you a few notes on Professor Liz-Marzán. He's the director of the SIC Biomagune in the Basque Country. He's also the group leader of the Bio-Nanoplasmonics Lab there. His research focuses on the synthesis of metal nanoparticles and colloidal chemistry applied to nanoplasmonics, the development of the fabrication of the composites, as well as their characterization and application for biomedical purposes. Luis is co-author of about 500 publications, 9 patents, and he has received several national and international research awards, including 2 ERC advanced grants. His H index is 121 in 2021. He's among the most cited Spanish researchers in material science. He's a member of the European Academy of Sciences, the Academia Europea, the Royal Academy of Exact Physical and Natural Sciences, Royal Spanish Society of Chemistry, the Royal Galician Academy of Sciences, the Royal Society of Chemistry, and correspondent of the Royal Academy of Sciences of Granada. He is also editor of the prestigious journal ACS Nano. And throughout his career, he has been awarded with different prizes, such as the Humboldt Prize, the Jaume I Prize in Basic Research in 2015, the Enrique Moles National Prize in Chemical Science and Technology in 2018, and recently this year, he's also received the Lilly Prize for Biomedical Research in the category of Preclinical Biomedical Research for his research in the field of nanoscience and nanomedicine. So we are really honored to have you here, Luis. Thank you so much, and the floor is yours.
All right. Thank you very much, Xavier and the organizers for inviting me to participate in this school. And of course, thank you, Agustin, for your always nice and kind introductions. All right. Let me see if I can share my screen. I guess it's working, right? Okay.
Yes.
Trying to use the laser. Okay, so I was thinking I'm going to try to provide 2 stories. If I get too long in the first one, you can cut me and I can skip the second one. Anyway, it was a bit difficult to decide how to focus this lecture because this is a master's school. And so probably a very general discussion on plasmonic nanomaterials and their properties and applications would have been appropriate. But I thought maybe I can give a brief and general introduction and then try to explain concepts along the way of recent developments in my lab and together with my collaborators. And so anyway, I'm sure you have seen something like this before, and the context of your research or the school, it's definitely very well known that nanomaterials have a lot of interest, not because they are very small, but because being small, they display properties which are very different in many cases to the properties of the same material in the bulk scale, but also that the properties can be manipulated by slight changes in the size and in particular in the morphology of the materials. And in reality, this is closely related to the changes in the ratio between the number of atoms that are located at the surface or the interface of the nanomaterial with its environment, and the atoms which are located in the interior. And so this is, I think, very clearly shown in these drawings here, because when the atoms are located or surrounded by other atoms, their properties are different to those which are on the surface, which are located together to other atoms in the inside, but they are next to a liquid or a gas on the outside. So the interaction forces change dramatically. And in the end, this affects enormously the overall properties of the material. And depending on the composition of the material we are discussing, the properties that are affected by the particle size or the morphology can be very different. And in the case of metals, or in particular materials with free electrons, some of the properties that are affected, because we could discuss others, are related to the interaction of electromagnetic waves with the electrons in the material. And so in the bulk, some electromagnetic waves may induce these propagating waves inside of the material. And this is usually the case for noble metals, where there are lots of free electrons. But if we reduce the dimensionality of the material to 2D, and we have a very thin film, then these charge waves cannot propagate inside of the material anymore because the wavelength is too long. And so they are confined to the interface between the metal and the dielectric next to it. If we reduce further the dimensions to very tiny particles, then in the limiting case of a particle which is spherical and several orders of magnitude smaller than the wavelength of the radiation, all that can happen is that you're creating a dipole which may oscillate in resonance with the frequency of the electric field in the incoming radiation. And so this is what we call localized surface plasmon resonances, and they are the basis for most of the phenomena that we know as nanoplasmonics. And so in the context of colloid science that Agustin mentioned in the introduction as one of my specialties or education topics, this means that when we have gold or silver small particles dispersed in a liquid, in water, for example, then they displace colors that are very different to what we would call silver color or golden color. And so silver nanoparticles, spherical in small sizes, display this bright yellow color, and gold particles display a red color. And this is correlated with very sharp absorption bands in the visible, which are, of course, the complementary of the color that we see. And so by changing the composition, but also the size and the morphology of the particles, we can tune the wavelength at which these resonances take place. But before going into that, let me, just one more point here. Apart from very intense absorption bands, the interaction of light with these very tiny metallic particles leads to the enhancement of the electric field at the surface of the particle in a very localized way, so that a few nanometers away from the surface, the field is no more enhanced. And so there are certain properties that can be changed when other molecules are located here at the places where the electric field is largely enhanced. And I will come back to this in a minute. I was saying, before going into actual properties, let me tell you one of the reasons why I started working in this field. When I was a postdoc already almost 20 years ago in Utrecht University in the Netherlands, there was an internal seminar where a speaker came from a company making pregnancy tests. And while explaining how pregnancy tests work, he actually carried a vessel with a liquid that he placed onto a heating and stirrer plate. And he started boiling the liquid and added another liquid. And suddenly the color of the solution changed into bright red. And so he was explaining that these maybe old-fashioned pregnancy tests work with a very porous stripe, which is dipped in the urine of the woman who wants to be tested. And then by capillarity, this liquid propagates through the strip. And then there are two windows. One is called the control window, which tells you whether the test is valid, and the result window, which tells you whether the woman is pregnant or not pregnant. And so the components of this test are schematically shown here. And so the interesting part that caught my attention is that the color that gives you the result and the validity of the test is coming from gold nanoparticles, which are coated with an antibody of the pregnancy hormone. And so when you dip the urine, if the hormone is present, it will bind to the antibodies. The particles will flow together with the liquid along the stripe. And then there are another two sets of antibodies in the test line and the control line, one which will definitely trap the particles if they have made it as far, and the other where the particles will only bind if the hormone is present, so in case of a positive test. And the reason why gold nanoparticles are used for these tests is, first of all, because they have enough surface to bind a few antibodies, so the reliability of the test can be higher than for standard dyes. And second, because the intensity of the absorption bands, of the absorption coefficient of these particles, is orders of magnitude higher than that of standard dyes. And so I would say this is one of the first real applications of nanotechnology, even before we were calling it nanotechnology. And of course, nowadays, there are plenty of tests, including COVID-19, that are based on the same concept and that simply you can apply by changing the nature of the antibodies on the gold nanoparticles. Anyway, we are interested in a bit more sophisticated sensing, mainly because we want to work on problems that require a higher sensitivity. And in this context, already, I would say more than 10 years ago, we started to work on something called SERS, which stands for Surface Enhanced Raman Scattering. And so Raman scattering is a spectroscopy technique in which you measure vibrational peaks related to the vibrational modes of bonds within molecules. And so the combination of peaks within one molecule will give you a sort of vibrational fingerprint that allows you to identify very selectively the presence of that molecule. The problem is that in the standard technique, the sensitivity is very low. So you need a large amount of material so that you can identify the presence. And this is not very good if you want to do highly sensitive detection. And so in the modality of SERS, what you do is you try to absorb your probe molecules onto nanoscale metallic materials. And then because when you are irradiating the plasma resonance modes, there will be an enhancement of the electric field at the surface, the polarizability of this molecule will be largely affected. And this translates into a large enhancement of the intensity of this Raman spectrum. And the intensity can be applied, can be enhanced in many orders of magnitude, even to the limit of single molecule detection, but only in very specific and optimized cases. And so it has been challenging to find which are the most appropriate enhancing materials to obtain the highest sensitivity. And so one way to improve the enhancement of the sensitivity of the Raman spectroscopy comprises manipulating the morphology of the particles that you're using for the enhancement. And the reason is, first of all, that you can manipulate the frequency of the light that can enhance the signal. Second, when you have elongated particles, in particular with sharp tips, like in these triangles or these that we call nanostars, then right at the tips, the intensity of the electric field is extremely high. And so if you're able to bring your molecule onto one of these tips, then there will be a very high chance that you will be able to detect that molecule in very small concentration. Another way to improve the sensitivity is bringing particles close to each other. In that case, there will be interaction, what we call plasmon coupling, between particles that are close to each other. And then you generate what we call hotspots in the very small gaps in between the particles. So that again, if the molecules are able to be trapped here, there will be a large increase in the signal. And this is exemplified in these two spectra here. So here we had a Raman active molecule in contact with isolated dilute gold particles in solution, and the enhancement was not sufficient to see clearly the spectrum of the molecule. By simply adding sodium chloride to increase the ionic strength of the solution and promote the aggregation of the particles, then you're immediately creating millions of hotspots like this, and they will be likely trapping many of the probe molecules. And then immediately you see this very well-defined spectrum where you can identify vibrational peaks corresponding to the bonds of the specific molecule. So this is a very useful technique which has a very promising future. In fact, we recently contributed to a large document which summarizes the present knowledge, basic knowledge, and applications of the technique. So if you're interested, this is a very long document, but it really provides a lot of information that you can find by looking at the different sections. Anyway, let me go back to how to manipulate the size and the morphology, because I was telling you this is one of the ways of improving the sensitivity. So if you want to stay into spherical particles, there are quite a number of techniques to fabricate spherical gold and silver particles. Gold is easier. And in fact, if you are skillful, you can even obtain these very well-defined, very spherical particles with extremely sharp absorption bands. And you can manipulate the particle size. But what happens when you increase the particle size is that first you have a sort what we call a red shift, so a shift of the position of the plasmon to higher wavelengths. And at some points, this resonance band becomes very broad, and you see a second band appearing at lower wavelengths, which corresponds to so-called quadrupolar plasmon modes in the larger spheres. The problem here is, first, the shifts that you can get require large increase in the particle size. And second, the shifts are accompanied by huge broadening, meaning that excitation with one specific wavelength is becoming less efficient. The alternative is working with anisotropic particles. And the most popular ones are probably so-called nanorods, where you have, first of all, different ways of exciting electron oscillations, depending on the relationship between the polarization of light and the orientation of the particle. So you can excite resonances along the axis of the rod or across the axis of the rod. And this means that you obtain two bands which are well defined. And in particular, the one related to oscillations along the rod can be manipulated through the anisotropy, so through the ratio between the length and the width. And this is quite nice because then you can select very finely which is the material that you want to use for a specific excitation with a laser wavelength. Also in these materials, there are some problems with efficiency because the spectra are actually broader typically than the expected one for monodispersed nanorods. And this is because inevitably there are tiny differences in the dimensions of the particles. Recently, we have shown that you can improve this by using ultra-fast lasers. So by femtosecond irradiation of freshly prepared gold nanorods, you can significantly narrow down the spectrum, and you actually can get optical signatures which are similar to those that you get for one single particle. But anyway, this is a quite complicated process. And this is why we decided to start working on the second alternative related to bringing particles close to each other. As I mentioned, this is related to the generation of new plasma modes when the particles are coming close to each other. And the energy of the new modes depends on the proximity between the particles. And so there is a theory that is called the plasmon hybridization theory, telling you that when the particles are coming close to each other, you're generating two new plasmon modes. And you could call this bonding and anti-bonding plasmon modes. And these are related to how they behave in terms of absorption bands and also near field enhancement. In any case, this is not very different to what we have shown already 20 years ago, where by using gold particles coated with silica and assembling them into very thin films, we could actually watch transitions from the color that you expect for isolated particles when the silica shell is thick enough so that there is no plasmon coupling, all the way to the color that you expect for fully aggregated particles. When gold particles are touching each other, there is no separation between them. And you can actually see here in this spectrum that this also allows us to tune the absorption wavelength in the full visible and coming close to the near infrared. Again, for a high density of closely touching particles, the corresponding band is extremely broad. And so we started thinking more recently that perhaps by promoting the organization of nanoparticles in a close to ordered manner, then we might get a sort of coupling between the effect of the plasmon interaction and the effect of ordering in the nanoparticle system. And so we were trying to improve the quality of the substrates for enhancing the Raman signal so that we can maintain the positive aspects of the technique. I told you already, selectivity, sensitivity, it can be implemented in very fast measurements. You can use portable systems. You can even prepare encoded nanoparticles. I'm not going to speak about this today, but there is plenty of work in this direction. And it can be applied on almost everything. Until recently, problems have been with reproducibility and uniformity of the substrates, and also with the need of having the probe molecules in contact with the metal surface so that they can fill the high electric field. Another problem is related to signal contamination, in particular in biofluids, because other molecules around can also bind to the nanoparticles, and then you can get extra peaks or even screen the binding of the probe molecule. Another problem that has not been very much studied is the so-called memory effect. And this is actually related to signal contamination, but can be described as the probe molecules absorb into the nanoparticles. And then if you want to analyze the same sample because it has changed over time, you may not see differences in the spectrum because the previously absorbed molecules are not leaving. And so you're seeing the same signal as you were seeing before. So if I manage to do it quick enough, I will tell you our approach to solving all of these problems. So I was telling you that we decided to try the assembly of particles in a controlled manner. And so we started using a few years ago something called templated self-assembly, which simply means that you prepare a template with holes, and then so you obtain something like this, and then you fill the holes with your nanoparticles like this. You let the solvent dry, and then you transfer these regularly organized particles onto a substrate, and then you can use them for analysis using the surface enhanced Raman scattering. And so we demonstrated that this can be done by organizing, for example, gold nanorods into these very well-defined so-called towers of nanoparticles, supercrystals, where you can see in this tomography image that they are perfectly well organized into rows, and there is a perfect or almost perfect organization in the full volume of each of the pillars that you see here. Related to other morphologies, we also demonstrated the organization of spherical particles into these pyramidal structures, which internally also have a very well-defined organization. And both of these morphologies demonstrated very efficient Raman enhancing activity, but they have the problem, or not the problem, they are not perfect because, first of all, they are very large compared to the wavelength of light. So it's difficult to exploit additional effects coming from the organization of the particles on the substrate. And so I'll try to explain that slightly more in a minute. And so this is why we decided to start working on smaller assemblies. And I should say that this slide was prepared before knowing that Agustin would be my chair today. And so anyway, Agustin approached me saying, we do have nanostructure templates with smaller holes and smaller inter-hole distance, so that if we're able to organize your particles onto a substrate, the same way you did with the other templates, then we might be able to obtain structures like this, where the inter-supercrystal distance can be of the order of the wavelength of light. And so we immediately started working on this. One of his students, Cristiano Matricardi, came to my lab, worked with my postdocs and students, and we managed to obtain samples like this, where you see these very bright colors, because the organization of the particles in these very regularly ordered arrays leads not only to plasmonic effects, but also to light diffraction. And light diffraction leads to very bright colors depending on the inter-particle distance and also depending on the illumination angle, the same way as you see in opals. So in opals, you have very bright colors, typically many colors at the same time, because you have crystals made of silica spheres of sizes around 400 nanometers, so that they actually diffract light, and the color of diffraction depends on the illumination angle. Anyway, so once we were able to optimize the fabrication of these structures, we started studying their optical response. And so in this case, what happens, as I was mentioning, is that the excitation of plasma modes in each of the clusters that we are organizing couples to the diffraction of light that affects the whole sample. And so in the end, we obtain something called Rayleigh-Wood anomalies. That means that we can now tune the position of the main plasmon resonance, so-called lattice plasmon resonance, through the lattice parameter, through the separation between clusters within the substrate. And this is very nice because now we can simply tune the fabrication through the masters that Agustin can very accurately prepare. And now we can prepare substrates that we can tune to the illumination wavelength that we like. So again, through experimental and theoretical modeling, we saw not only that we can predict the position of these lattice plasmon bands, but also that we can see that the coupling between the different modes that we are exciting leads to extremely high electric field enhancements at the gaps between the nanoparticles within the clusters. Regardless of the morphology of the cluster that we are organizing, the enhancement is typically much larger than what we obtain for disordered arrays. And so now we simply have to fabricate the templates so that they are absorbing and matching the laser wavelength that we use to excite the Raman spectroscopy of the molecules that we want to identify. And so within this ESC project for the biocells, where we are trying to demonstrate the possibility of monitoring the behavior of tumors during their growth in vitro, but in realistic models, we decided to apply, of course, these very nice superlattices to analyze some of the metabolic processes that take place specifically in tumor cell lines. And so mainly driven by my student Javier Plou, working together with other students and Agustin's group, we started to get these superlattices and to study the enzymatic process of conversion of tryptophan into kynurenine. These are metabolites that are specific of several cancer types, and they had display these characteristic peaks in Raman spectroscopy so that we can distinguish one from the other. And in fact, if we measure mixtures of the two metabolites at different ratios, we see that depending on the ratio, we can see one peak decreasing, the other peak increasing. And this makes us think that we might be able to, using these substrates, to monitor the conversion of the metabolites in situ during tumor progression. And so we started to grow HeLa cells. These are very typical cancer cells that can be purchased and which overexpress the enzyme called IDO+, which is actually converting tryptophan into kynurenine. And so we were able to study the conversion during time of tryptophan into kynurenine by again watching the decrease of this peak, the increase of this peak. And this was only possible thanks to the particularly intense enhancement of the field that we obtained with the superlattices. I should also indicate that this study was carried out by extracting the supernatant from the tumor cell culture and then placing a drop on top of our substrates and measuring outside of the contact with the cell culture. Which is not optimal because this is a little bit invasive and it's also taking a longer time. You cannot do it in situ during the process. But it's related also to overcoming potential problems, because if tryptophan would bind to our substrate and we were measuring the signal over time, it was likely that this peak would remain as intense because the molecules would remain attached to the nanoparticles. Another derivative study was related to analyzing the correlation between Raman spectroscopy of metabolites and the death of cancer cells. And so it is known that when cells die, they release so-called purine derivatives. And so we designed a sort of cancer-on-a-chip model where we had the cancer cells incubated in a microfluidic gap. And then we placed on top a glass slide with the nanoparticle superlattices so that we could illuminate from a laser directly the substrate in contact with the fluid, which is the supernatant of the cells. But we are not removing liquid, we are studying directly next to the cells. And so by doing this, again, we could see the correlation between the disappearance of tryptophan and the formation of kynurenine. But during cell death, we were observing the formation of this peak, which initially we called unknown, but then we related to the presence of these purine derivatives. And in fact, we could again monitor this process over time and correlate cell death to the intensity of this peak that was appearing here. Now, as I was mentioning, this study was only possible by using many substrates that we were using one at a time. Let me just show you very quickly how we were doing this. So this is the process for removing the substrate from the contact with the cell culture. You have to be extremely careful so that you don't stress too much the culture and you don't remove the liquid. And then you have to place a clean substrate directly on top. And again, you have to do it extremely carefully because otherwise you will affect the cell culture and the supernatant. And so this is what we had to do to avoid memory effects. Until Javier and another student, Matthias Chaconnay, came with the proposal to use a polymer layer which could be spin-coated on top of our superlattice array so that we could protect the nanoparticles from attachment. So again, this is another demonstration that if you're not doing that, you may have the Sear's memory effect. So this is a standard array with no polymer on top. And so we first incubate with mercaptobenzoic acid, we obtain this peak. If we then remove the liquid and incubate in another analyte, nicotinamide, then we actually see a small peak that we were almost actually observing here without nicotinamide, where we expect the signal of this molecule, but we still see mainly the peak of MBA because the MBA molecules are still absorbed on the particles and they don't allow the new analyte to bind to the particles. If we repeat the process by incubating with a mixture of the two analytes, we see exactly the same effect. We only observe the presence of MBA. With the new technique, what we do is first fabricate the superlattice array, then speak code with a polymer PLGA, and PLGA is selected because it's known to be thermosensitive. And so what we do is then illuminate with a high intensity laser so that we are creating a hole in which we can measure the signal of molecules that are attaching exactly at that time onto the particles that are now accessible to the problem solution. And so again, if we measure before opening the gap, we see nothing. After we open the hole, we see this peak, which is representative of MBA. Now, let me show you how it works. So how it works is another property of the nanoplasmonic materials, because when you are irradiating with a sufficiently intense laser, you're actually promoting localized heating. As you can see here, these are pictures taken with a thermal camera. So what it means is if you illuminate the substrate outside of the area covered by nanoparticles, you see no heating. If you illuminate in the area with nanoparticles, you see a very sharp spot, which indicates strong heating in that spot. And it works the same when the substrate is immersed in water. So when you're promoting this localized heating, what happens is that you're opening holes like this, and then the nanoparticle superlattices are again accessible to the solution present at that specific time. So once we have this, we can repeat the same experiment. So we first measure MBA, then we remove the solution, we open another hole, and now nicotinamide molecules are absorbing on this new spot. We measure right here, and now we see this peak, which corresponds to nicotinamide. And then with the same substrate, we can still open another hole and measure a mixture of the two analytes, and now we see both peaks at the same time. So we are effectively resolving the problem of the pre-adsorption of analytes because we are measuring on a different spot that is generating at the time of the measurement. And so you can see here, we can also do mapping after opening the hole. You see there is absolutely no signal around the spot because here we still have the polymer film, and there is only signal at the spot where we have opened what we call the measurement window. And we can do this also within a microfluidic chip so that we can alternatively flow either water or solutions of different analytes, in this case, mercaptobenzoic acid again, and thiobendazole, which is a well-known contaminant in crops. And here you can see, by simply changing the solution we are flowing and opening holes at every different time, we can see signals that correspond to either thiobendazole, then nothing because we flow water, then thiobendazole again, water again, and now we flow MBA and we see the different signal, and we can obtain signals corresponding to what we are flowing at each specific time. And this is very versatile, for example, for monitoring environmental waters or monitoring some biofluid that you want to analyze. More specifically in biofluids, and coming back to the previous story about monitoring tumor growth, this is another application where we demonstrate the effectivity of this process. Again, we have tumor cells incubated in the microfluidic chip. In this case, we were studying a slightly different metabolic conversion from adenosine to something called hyperxanthine. And again, we add a promoter of the expression of the enzyme. And by carrying out the analysis, let me show you. So if we are using the same substrate without the PLGA treatment, we only see the peak corresponding to adenosine, both at 0 hours and at 24 hours. If you trust the result, this would tell you that you either don't have a tumor growing in the system, or it has not expressed the enzyme that promotes this metabolic conversion. However, if you do the study by taking the supernatant and analyzing outside, you can see that the signals at 0 hours and 24 hours are very different and confirm the presence of the tumor cells and the conversion of adenosine into hypoxanthine. The same result is obtained by using this new system where you're opening different windows at different times and measuring at different spots exactly what is present in the supernatant of the tumor at a specific time. Now, I'm going to switch gears. Agustin, if I'm going too long, you stop me at any time. So the second story I wanted to tell you is related to something that we call plasmonic chirality. This is perhaps a more recent field of study and is related to, what most of you know as chirality. It is very standard in molecular systems, in particular in organic chemistry. It's also very important in biomolecules. In fact, some of the most popular drugs are only effective with one of the enantiomers and not with the other. And so anyway, the point here is that we have structures that do not have inversion symmetry, meaning that you cannot superimpose their mirror images exactly the same way as you do with your hands. So they are mirror images, but if you try to superimpose them, it's really impossible. And so when molecules display this property, very often they also absorb differently light which is circularly polarized to either to the right or to the left. And this converts into a property that is called circular dichroism. In nanoparticles, typically we have symmetric structures, so that illumination with either linearly polarized light or circularly polarized light of any handedness would not make a difference because there is full symmetry and the interaction of this light makes no difference. So it has been proposed that if you can fabricate particles with geometrical chirality, then you can also obtain circular dichroism because of the different interaction of circularly polarized light, either polarized to the right or to the left. And this is related mainly to chiral changes in the refractive index close to the particles. So there has been some work related to making chiral particles. I'm going to show you very quickly. So the first really impressive piece of work was published by the group of Kitai Nam from Seoul National University a couple of years ago. And they basically did the growth of gold cubes and octahedrons in the presence of a chiral amino acid. And they were able to promote the formation of these very nice structures, which definitely display a structural chirality. And they can also display very high circular dichroism signal. Another example was coming from our lab more recently. Last year, we published the chiral growth on gold nanorods. So by adding a chiral molecular additive to the surfactant that we typically use to stabilize these particles, theoretical analysis tells us that you can obtain this sort of helical or quasi-helical micelles, which can also wrap in a quasi-helical manner onto the nanorods. And then by reducing a gold salt on top of this system, you can obtain particles like this. If you don't look carefully enough, you may not see the quasi-helical structure. I think it's most clear in this bigger particle here, but it's also quite revealing that if you measure circular dichroism, you can obtain extremely efficient signals even close to 0.2 or even in the infrared 0.3%, which is almost the record intensity in this type of properties. But also, depending on the geometry, you can tune the position of these circular dichroism signals. Anyway, I cannot tell you yet about applications of these particles because it's too early, but I wanted to tell you about application of a different strategy, which is related to organizing non-chiral particles into chiral structures. And so there have been lots of works related to using mainly DNA structures, DNA origami typically, to organize either spheres or rods into quasi-helical typically, and in any case chiral structures, so that the structure globally would have also the circular dichroism signal. And so, inspired in these works, a very skilled postdoc in my group, Yatish Kumar, obtained a Marie Curie fellowship to study the possibility of analyzing and understanding the formation of so-called amyloid fibers by using plasmonic chirality. And so the background is amyloid fibers are known to be related to many of the most devastating neuro disorders. And the reason this happens is that these proteins, the so-called amyloid proteins, may get scrambled in the body, and then they start aggregating, forming small aggregates, then they forming linear beta sheet oligomers, and then growing into so-called protofibrils, and ultimately into very long fibers, which can accumulate in certain parts of the brain and start damaging cognition and memory and a few other things. And so if we are able to detect the formation of these fibers at low concentration and very early stages, we might help finding new techniques for diagnosis and therapy. And so from literature, we knew that some of these amyloid fibers form sort of double helix structures. And so we proposed that if nanorods could adsorb following this double helical structure, then we should be able to see circular dichroism in the infrared, which is very different to the circular dichroism of the fibers themselves or other biomolecules in solution. And so we started working with alpha-synuclein as a model system. The protein was expressed by our colleague Aichiber Kortajarena, and they were also in charge of incubating them in the conditions that they form these elongated fibers. And so, trusting the literature studies related to the double helix structure, we decided to start probing the possibility of forming the fibers incorporating nanorods. And so Yatish started incubating nanorods with the native protein, but unfortunately, there were almost no changes in the linear optical activity, and there was almost basically nothing in the circular dichroism spectrum, meaning that there is no chiral organization. By increasing the concentration of protein, he started to see some changes, but these again do not seem to be related to chiral morphologies until he decided to first incubate the protein and then incubate with the nanoparticles. And so by incubating the particles with preformed fibers, he started to see this redshift and broadening of the plasmon resonance, but more important, the formation of these very well-defined circular dichroism curves, which actually shift according to the shift of this plasmon resonance. And so by extracting samples at different times and measuring the circular dichroism, we obtained this sigmoidal signature, which is typical for this protein aggregation process. And then by watching the samples in the electron microscope, we could see the formation of elongated arrays of nanorods. And if we are hopeful enough, we can see in some places actually that these arrays of nanorods are crossing each other, which might mean that we are having a double helical structure. Confirmation only came thanks to the assistance of our colleagues at the University of Antwerp, who are world experts in electron tomography, and they provided us with these very nice cryo electron tomography movies where we can see actually close to perfect double helical structure. We then did theoretical modeling, and then we demonstrated that the experimental signal that we see is very similar to the calculated one when you take into account the polydispersity in the formation of these double helices. In order to show the potential application, we started working with our colleague Joaquin Castilla in CSC Biogune, who is an expert in neurodegenerative disorders, and he had access to the biobank in Bilbao. So he actually obtained 4 brains from dead people, 2 of them dying from something different, 2 of them dying from Parkinson's, because Parkinson's is known to be related to fibers coming from alpha-synuclein. And so they started doing the extraction of the so-called substantia nigra, where these fibers are known to accumulate. And they did something called homogenization and purification of these extracts from the brain. And then Yatish went and incubated the nanorods and measured the optical and secular dichroism signals. And surprisingly, this worked very nicely. So in the standard localized surface plasmon resonance optical signature, we see that in the control brains, there were basically no changes, meaning that the rods are probably attaching to substances around, but not aggregating. In the Parkinson's brains, there was this slight redshift, but clear broadening. And in secular dichroism, the control brains only showed a signal that can be ascribed to the noise. But in the Parkinson's brains, we see very clear signal coming from the secular dichroism of the nanorods. And so this can be seen as a preliminary study that shows that we might be able to contribute to understanding these processes, and also that if we are able to find other biofluids that are easier to extract than brain samples, then we also might be able to come up with a sort of early stage diagnosis of this process. With this, I finish. I think the conclusions have been quite clear. Maybe the take-home message is that if you're able to prepare suitable platforms made of plasmonic building blocks, then you can be able to monitor important problems in biological systems. But it's very important to understand the optical processes, and numerical modeling is also helping a lot in this context. I'd like to thank you for your attention, and collaborators and funding agencies for making this work possible. Thank you.
Thank you so much, Luis. Very, very nice presentation. We would like to have some questions from the audience. So,
should I stop sharing, or
maybe there's some questions that are regarding the presentation, so okay. we can leave it up. So let's see. I see a couple of hands up. Victoria, would you like to ask your question directly?
Yes, thank you so much for your extremely interesting lecture. I had like a lot of questions in the beginning, but you were answering them one by one throughout the lecture. So thank you again for organizing it so nicely.
Good.
And well, I still have a lot of questions to you.
Please feel free to email me, anybody after the lecture. I will be happy to answer questions if I can. But anyway, please go ahead.
Okay. So could you please comment on the first on the possibility of like the similar kind of order to the crystal structures like you were talking about, but the inverse ones? I mean, namely using nanocavities in the metallic film instead of the self-assembled agglomerations of the nanoparticles on the dielectric substrate. Sure. And will it affect the coupling effects of the plasmonic and photonic bands?
Yeah, there has been actually a lot of work related to similar substrates with basically having the metal as the medium and holes creating the structure. And you can obtain similar effects. What I think would be missing in that case would be the hotspots between the particles. So let me clarify that we are not the first organizing particles in this way, but most of the work that has been done in this respect is related to organizing single particles. And this can be done by either using lithography or similar methods to what we were using, but using single particles in each of the spots. And this is very nice, and you can obtain high quality lattice plasmon bands, but there will not be a large enhancement of the electric field because you are not creating the hotspots in between nanoparticles in the clusters. And I probably don't know enough detail of the work related to the crystals, but I would expect a very similar effect.
Okay.
Thank you.
Thank you so much. And if I may.
Sure.
I mean, the chair has to say, I don't know what the time is.
Let me, Victoria, can I put you on hold so we can continue, other people can ask questions?
Sure, of course. Thank you so much.
Thank you, thank you. Fabio, would you like to ask a question?
Sure. I hope you all can hear me, and good morning, everyone.
Yes.
And thank you so much, Professor Luis, for, I think it was a great way to start. I really enjoy your talk, even though I'm not so much into this field, I could enjoy. So thank you very much for it. Also, I'm more related with the bio part, so I'm very curious about the experiments regarding the tumor growth and the tumor environment. I'm quite curious, and I have just a short question, which is related with the time that the PLGA polymer that we use needs to recover after the laser treatment.
This question shows that I did not explain well enough. So let me explain again. The polymer does not recover. So what we do is we open micron-sized holes, apertures in the polymer, but the rest of the film is completely stable. And so what we do is we simply shift a little bit the position of the laser with respect to the substrate, and then we open another hole. And so the holes remain, but we never measure again in the same hole. Does this answer your question?
Sure. However, I think this is a quite interesting and I would say elegant from the scientific point of view. However, if we think about clinical applications, where I might see it a bit complex since we need to put a laser or something like that. And if we think about the first example that you show about the pregnancy test with the gold nanoparticles and the antibodies, I was thinking if instead of looking for the tumor growth information, if you could try to have specific antibodies for specific antigens to have a screening of the kind of cancer someone might have by a drop of blood or something like this. Do you think this would be possible with your strategy?
Yeah, but again, we are talking about different problems, and this is again my fault. The objective of the work that we are doing is not really, at least for the beginning, it's not really doing diagnosis. So what we are trying to do is we are trying to create 3D tumor models which resemble real tumors, and then to study in situ, in real time, and with spatial resolution, the changes that are related to the behavior of the tumor under different environments. So this is a much more fundamental than what you are talking about, which is also very important, of course. So we are, at least in the first stage, again, we are aiming at providing doctors with information about how the tumor should behave depending on the conditions that they promote. And so we see a clear application, if we manage to do it well enough, into drug screening, because if you're able to provide reliable information about the survival of the tumor by using different drug candidates, then you may be able to select the drug candidate by avoiding, at least in good part, animal studies. And what you're proposing is definitely possible if you have a clear biomarker of a specific cancer, and then you can do a biopsy and study a fluid where this biomarker has to be present, that should be possible.
Perfect. Thank you very much.
Nithya Priya, would you like to ask your question?
Yes. Sorry. Hi.
Hello.
You for a very nice presentation. It's very interesting, and it was very interesting field to follow as well.
I hear you very low.
Yeah. Could you speak up?
Thank you for the very nice presentation. I'll ask super quickly. It was regarding the preparation of the particles itself. How much was the error between the size of the particles in the template? And does it vary between the conventional preparation and using a template? What was the size difference you can see, and how it is affecting the chirality or the plasmic resonance of the particles itself?
Oof, I think I got lost. So the first question was related to making the superlattices and how much area we can cover.
Oh no, what was the difference in the, what was the error in the template of the different like nanodots you obtained in your template?
I'm not sure I understand.
The error, I guess, it's the error of in the structure you can make.
The error?
Yes.
You said it was around 400 nanometers.
Yeah, 400 nanometers is the separation distance between each of the nanoparticle clusters on the substrate. And this is defined by the template, which is made very accurately. And so there should be no significant errors in the positioning of the particles. There are certain differences in the specific organization of particles in each of the clusters, but we have found by theoretical analysis that this is not very important at the time of defining the lattice plasmon resonance.
Okay, thank you.
Thank you. So, any more questions? Victoria, this could be your opportunity.
Thank you. One of the other questions I had is a little bit more general, but you were talking about of course, the SERS application, which is the most logical for this kind of structures, but I don't know, maybe you have applied these structures in some other kind of applications, taking advantage of other effects like consequences of the plasma resonance, like hot electron formation or something like this.
Right, so we are not working on other applications because we are in a biomaterials institute, and so we are focusing on this field. But definitely there have been people, for example, Professor Terry Odom has been working a lot on obtaining lacing from similar structures. And this is also very important. Having a well-defined structure for creation of hot electrons and doing catalysis on a surface would be also very important. I think in that case, it's even more important that the particles are well retained by the substrate. So you should be very careful that the structure remains, because again, the local effects will be very important. Heating can also be applied, because for example, still in the biomedical field, there have been also proposals for using this type of effects, for example, to kill bacterial biofilms. And so if you have a highly sensitive surface that you want to protect, you might be able to modify it with similar template structures like this. And then by irradiating with an intense light beam, then you might be able to remove biofilms if these are affecting your application. So yes, I think that there are quite a few areas where this could be applied. And of course, the process is not limited to plasmonic particles. And so, well, we have been collaborating with Agustin, but he has also been doing other materials. For example, we reported the organization of perovskite nanocrystals, and here you can also obtain lacing by optimizing the structure.
Okay, thank you so much.
Okay. Any more questions? great opportunity, guys. Come on. So maybe Luis, could you comment on the perspective on where the field of SERS is going to go, or where are you planning to take it now, since it's been around?
Yes, well, we are working on several projects related to SERS. One I tried to explain already, and I think this is a very challenging one. So I only told you the part related to the, so to say, easy detection, because even though we are culturing the tumor cells in 3D because they are forming aggregates on the substrate, we are only looking at what happens outside of the cells. There is another part of the project which is related to using 3D printing of hydrogels doped with nanoparticles, so that we study similar processes but within the tumor and at different spots. And this is very challenging because we need longer penetration of light through the biological system. We need a very efficient response from the nanorods or whatever nanoparticles we use, but now they are not nicely organized within the scaffold. And we have to be able to show that that the changes that we see correlate with what is really happening. And so this is very ambitious, and I think we are going in the good direction, but it's still too early to say we will have a product. Another project is related to monitoring environmental waters, and so this is well, of course, a very important problem, but even more important or more worrying is that the regulations are constantly changing. And so more and more contaminants are actually included in the list of contaminants every year or every half a year. And some of these are very difficult to identify by other techniques unless you take the water and go in a lab and do the analysis. And so together with a company, we are trying to develop a system that could be used at the spot, so that you could monitor environmental waters remotely. I think this is, again, a very important problem to resolve. And then we are also working, as it was also proposed here, on sensors to actually diagnose diseases. And we are, well, I cannot tell you very much, and actually you do know, but we recently filed a proposal related to a very specific diagnostic test initially for COVID-19, but could be also for other diseases, which combines SERS with other biological manipulation techniques.
Thank you so much. Thank you. So is there any other question? Oh, Xavier.
No, Xavier is clapping.
Oh.
I just wanted to congratulate Luis, because he has really made a very attractive talk even for non-experts. So we are really surprised at how amazing is the kind of applications that you have advanced for these plasmonic nanoparticles that were a few years ago completely unknown, and now you have gone so far.
Thank you. I should tell you that part of my decision to show new data is that you have seen quite a few of my talks, so I didn't want to repeat everything.
Thank you very much.
Thank you. So if there is no other questions in the chat or YouTube or somewhere else, I think we could thank Luis for his presentation, for his time. Thank you so much.
Thank you.
Our privilege to have you. Thank you. Bye. So I think this is it for this session, right?
Thank you, Steve. Thank you for your help. So guys, I hope you like the talk. Now we have our break. We have no lunch because everything is virtual, so sorry for you. But see you at 3:30 p.m. We will continue. So at 3:30 we have our technical and interdisciplinary talks with Stefano Ossicini at 3:30, and at 4 we have Gemma Rius. And then we will continue with more plenary talks. So I will see you again here in the same Zoom session. We will use the same Zoom account the whole week at 3:30. If you have any questions, now is the time. And I will, before we all go, I was checking the attendance list of the people, and I will say the names of people I haven't seen in the participant list. If you are here, tell me, it's now the time to tell me, no, I was in the talk. So I don't have Min Yue Wang, Juan Tan, Jose Maria Castillo, Min Hua Kong, Wen Chao, Joselina Ibarra, Manel Mas, Linda Sheila, Akim Koboto, Paolo Flores, and Marita. I don't have you. If you were here, let me know, and if not, see you at 3:30 p.m.
I'm here, Marita.
Okay, thank you, Marita. I was emailing you now.
Yes.
So see you guys.
So now it is my duty and pleasure to introduce to you Professor Stefano Ossicini from the Università di Modena e Reggio Emilia. Stefano is an old friend and collaborator of mine. He has made his full professor at Modena in Italy, Modena and Reggio Emilia, because his university is split into two cities. And he made important contribution in the field of semiconductors, particularly confined semiconductors such as nanocrystals or nanowires. But he's also a kind of a transversal humanist, like we don't see so frequently nowadays. He wrote a book during a novel together with his daughter during the lockdown. Previously, he also wrote a play on Marie Curie. And today he will tell us about science, but not directly about his scientific work, but it's something that started as a PhD course on ethics in science, then became a book. Unfortunately, I guess it's only available in Italian. And now you have different format of this book in a talk. And today we will be hearing about one of this version. So Stefano, the floor is yours. I will let you know when your time is over, but in principle you have like 25 minutes ahead. Thanks.
Okay. Can you see there? It's okay? Okay, so I can start with this talk. You see, I will speak about science, in particular about integrity, misconduct, and the modern structure of scientific research. The reason is simple, because the starting point is the definition of science given by the American Physical Society. You see that what is important in order to have good science are two simple principles. The first one is the requirement about open exchange of data, procedures, and materials. So science must be free and must be also submitted to independent testing. The role of peer review is quite important in science. And also the researcher must also be able to abandon or modify accepted conclusion when they find that there are more complete or more reliable experimental or theoretical data. So these two simple principles, it seems that we don't have any problem in science, because the structure and the organization of science by itself is capable of self-correction. This was the reason that in the 80s, there was in America and USA a lot of cases of misconduct in science, especially in the case of medical science. And so there are a lot of scientific society, they adopt some ethical statement about science, but you see that the American Physical Society wrote in the 80s that the American Physical Society is one of the few professional societies which has not felt the need for the formal code of ethics. So you see that physics are so hard as science that it's not possible to, we don't need to have an ethical code for physicists. And even you see there is a book written by Steven Weinberg, which is Nobel Prize of Physics in the 80s. He wrote very beautiful books about dreams of a final theory. And he wrote, to the best of my knowledge, there have never been an important case of falsification of data in physics. But only 10 years after, what happens that in 2002, at the end of 2002, the American Physical Society decided to adopt an ethical code. The reason is simple, because the 2002 is quite important in physics because it's the year of physics fraud. What happens in 2002? In 2002, there was several cases of fabrication of data in physics. In particular, there was two very important cases. One is related to the discovery of super heavy elements, new elements in the elementary tables, elements 118, and it was discovered that data was fabricated in this case by this scientist, Victor Minov, at the Berkeley laboratory. The Berkeley laboratory are very well known. Several Nobel Prizes were given in the last century to these laboratories. And another more important case was at the Bell laboratory in 2002, in the same year. It was involving Jan-Henry Schön. Jan-Henry Schön was a German scientist. We moved in 1998 to Bell laboratory. He works in a group of Bertrand Bartlog in organic, nano-electronics, and semiconductor physics. And he wrote a lot of very beautiful publications. He was a sort of wonder baby because he was very young, and he published in 2001 45 publications, one every 8 days. Other publication that was 8 Nature, 5 Science, and so on. And at the end of the year, a commission discovered that all the data were data that were fabricated by Jan-Henry Schön. So there was the reason that now also the Physical Society is adopt the decision to adopt an ethical code. And my idea at the time was to understand what happens in science in the year they go from the middle of the last century to the new millennium. And the idea is that the question is, are we in presence of a changing number of misconduct in science? And if the answer is yes, in my opinion, the answer is yes. Why we are in presence of a mutation in the number and modes of scientific misconducts? My idea is that in order to understand what happens in science now, we must look at the kind of transformation that appeared in science in the last, I would say, 40 years. And I suggest to you the lecture of these two books. The first one is my book about fraud in science. Unfortunately, it's still only in Italian, but I hope to make a translation of this book in the next years. And there is also this other book that is written by Gianfranco Pacchioni, a chemist from Milan University. It's more or less on similar question. It is in English. It's the overproduction of truth, passion, competition, and integrity in modern science. So if you look at what happened in science in the last century, we can start from looking at this picture. The first one is very famous. This is the Solvay conference in 1927 in Brussels. And you see there was less than 30 participants, 29 participants, and 17 are Nobel Prizes. Now, if you look at what are scientific congress today, you see that normal American Physical Society, you have every year 4 congresses with more than 10,000 participants. And we have also normally congresses with more than 50,000 participants. This gives you an idea what are the change made in the scientific community in the last year, especially in the last 40 years. Another interesting point is related to the number of scientists hired in university, research center, and industry. If you look at last century, in 1930, there was 200,000 scientists, over 2 billion people, which means one scientist every 10,000 inhabitants. Now, we are more than 10 million scientists, over 7 billions of people, which means one scientist every 700 inhabitants. And this means that now the competition is really very tough. And if you compare the increase in the funding for research and development, you see that the growth of the research and development funding is at slower rate with respect to the number of scientists. This means that there is a much harder competition for research funding, and you know exactly that there are several research programs where, in order to have a success, it's like a lottery. If you look at the program of the European Union, you have about 2–3% of success rate, which means it's really a sort of lottery. This makes a big difference with respect to the past. And another important point is related to the difference in the composition of the research groups. The research groups becomes larger and larger. The aims of research becomes less transparent. Is clear only to the boss of the group, not so much to all other people in the group. And we have also that in the groups, the people that are working with short-term projects are more or less the people that do really research. I have compared here, for example, data for the Italian university. In 2016, we have that about 30% of the people working at the university are people with short-term contracts, 1–2 years, maximal 3 years. And in the case of Italian National Research Council, we have that the data for 2017, and you will see that we have 40% of the people, they are people hired with short-term contracts. So they are people with precarious condition, and then the people that are really involved in research, because a lot of people with permanent position, they have a lot of duties. This means that there is also change with respect to the people that are making the bulk of science now. And another interesting point is related to the answer to this question: how much do we publish? I think we publish too much. You see what happens with the growth of papers. You see that we have an exponential growth of paper starting from the 80s until now. And if you compare the topics in the titles of the paper, you see that the linear growth of ideas, the growth of ideas is linear, not exponential. This means, in my opinion, that we have a lot of papers. There are also papers that are not fake, but they are papers that perhaps are not so important, because the growth of ideas is much slower with respect to the growth of the papers. We have today about more than 3 million scientific articles per year, which means there is 6 articles per minute. They are published in journal with peer review, in real journal. And this is also an important point with respect to the fact that it is difficult to control for a single researcher also is a research field, because you need to read really a big amount of publication. And so this makes a difference with respect to, we will see what happens with respect to plagiarism and falsification of data and other questions. Another point is related to the number of papers with a lot of authors in the paper. If you look, the number of papers with more than 50 authors is increasing very, very fast. It's the blue curves here. This means a lot of critical inflation, because it's quite difficult to say in some paper really what is the contribution of the people they are between the authors on the paper. This is a famous paper, which is also Nobel Prize, because it was the paper related to the discovery of the Higgs bosons, and they appear in Physical Review Letters. And you see that there are 24 pages of authors in alphabetical order, and only 2 pages of articles. And it was a paper written by more than 5,000 researchers coming from more than 300 different institutions. So it's also what is exploding in the last years is the so-called honorary authorship. Honorary authorship means that there are some authors in the paper that really do nothing with respect to the argument in the paper. And there is a survey of the British Medical Journal, because this problem is quite important in medicine, where they see that in 25%, one article of 4 contains some authors that are really nothing to do with the paper itself. If you look at the increase in the number of journals, also this is quite amazing what happens in the last 20 years. You know that what is really important in science is the peer review. Peer review, I say, is like democracy. It's not the best method, perhaps it is, but it's the method that best works now. And also peer review is the method that makes science for us important, and also we can trust in the most of the results that we see appear in the journals. But it's really more and more difficult to cover all the published paper in the different journals. Now, this is the data for some years ago. There were more than 33,000 scientific journals with peer review. Now are more than 40,000. And in this data, there are not open archives, conference proceedings, and other means of communicating results. This means that the amount of written report on science is more and more growing. It's quite difficult really to follow what happens in different areas of science, but sometimes also in the area that you at best control. And this is my personal perspective. In the 80s, at the beginning of the 80s, I was in Berlin, working in Germany, and I wrote this paper with Frank Forsman about some pseudo-potential calculation. It appears in a journal related to chemical physics. And if you look in the 80s, 1980, one issue of Journal of Physical Chemistry contained about 30 papers, which means that in a year, this journal, only this journal contained about 3,500 pages. So it's possible to read 3,000 pages in 1 year. Now, the same journal appear divided in 4 different parts, A, B, C, and letters, and there are about 200 issues in the years, which means that you have about 70,000 pages per year, which means that really it's impossible to follow what happens only in this journal. And we have more than 40,000 journals. But this is related to the so-called peer-reviewed journal. But what happens in this millennium is that first of all, that also for very important journal like Nature, Cell, and Science, we see that the Nobel winner, for example, in this case, Randy Sheckman, is Nobel winner in medicine, declares boycott for these top science journals because he said that they distort the scientific process because they are more interesting, like is written here, this sentence by Anderson, Nobel Prize in Physics. They are interested to good selling science. So more interested to fashion, I would say, that really interesting science in some cases. The Jan and Schoen case was a good example. Most of the papers of science of Schoen appear in Nature and Science, and sometimes also against the opinion of the peer review, because it was science really interesting for the reader, really at the top of science, but unfortunately was fake science. But there is another important phenomenon which is really relatively new, which is started in 2000. They are the open access journals. Doa J is the directory of open access journals. And you see, the first one appeared in 2000. Now there are about 15,000 in 2021. And these are journals where you don't pay the subscription to the journal, but you pay for the publication. the publication are directly paid by the author. There is no copyright, so the study can be immediately made public and available to everyone, which is quite important from the point of view of spreading of science. But it's also, there is some problem related to the fact that with respect to how really these journals are really journals where the review is made in good through good work or made in some wrong methods, because what is important is to have the money for publishing the paper. And this is also some very important problem, which is related to the so-called predatory journals. Predatory journals, they are journals open review. They are really made only in order to do money. And this is an example. This is an example. There was Science there some years ago. Some journalists of Science invented the name of the researcher, Okarlofo Kobange, which was a researcher at the Basse Institute of Medicine in Asmara. And the researcher is fake, they don't exist. The institute, they don't exist. But if you look, they submitted this paper. This paper was about the marvelous properties against cancer of some lichen, and it was accepted in few weeks by the more than 50% of the journal where the paper was submitted. And if you read the paper, it really was made using the computer without any really important data or meaning. But this is a demonstration of what happens with this number of journals, which are quite a lot, because there is a list. This is the so-called COBL black list of predatory journals. There are more than 10,000 journals. And they are all journals, they appear. They are journals with the ISBN number. They are journals that you do find on the web. And if you look at this journal, most of them are related to some country. You pay for the publication, you have your article which is published. And there is another important question which is now related to the so-called predatory conferences. Every day I open my email at the university and I have some invitations to some conference in Bangkok or in Italy or in Greece, in some beautiful place, but they are conferences made only in order to make money, but they publish also the proceedings of the conference. So it's another situation where the number of publications grows and it's quite difficult to control the quality of this kind of publication. I come now to some very important point, which is related to the so-called science metrics. Now we are in presence of a lot of different indicators for scientific performance. And the problem is the so-called effect of this kind of performance indicator. In principle, at the beginning, all the indicators are meaningful. It means that, for example, impact factor, in order to see a journal which is important, it has a big impact factor, 3, 4, 5, and so on, or 50 in the case of Nature. But the problem is that every time that you make some measure, their community is very able in order to organize itself in order to be in favor of this kind of measure. And so what happens now that we have now impact factor, we have H factor for the single researcher, the E10 index, which is the citation of your work in the last 10 years. We have the ranking of the university. All this kind of measure, they have produced not only good effect, but also very bad effect. One example is salami slicing. Salami slicing means that normally when I started my career, I published one paper in 1 year. It was more than 40 years ago. And now the same paper, you can divide this paper in 5 different publications. So you have the same amount of information, but divided in 5 different papers. And then there are also methods that are really bad, like collusive citation. I decide to cite my work in my friend, and my friend decide to cite my work in his paper. There are also sometimes coercive citation, which means that is a request for the journal to cite in your paper publications which are published in this journal, because this improves the impact factor of the journal itself. There is an interest paper appeared in Nature some years ago. They make some discussion with more than 150 researchers, and more than 50% of the researchers declared that they have changed their behavior with respect to the publication, of their results, in order to be good with respect to the index. This is some very interesting example. This is a paper appeared some years ago. This is a paper that had more reference than words. The papers contain about 200 words. It contains more than 200 references, and all the references are for the first author of the paper. This is an author which has an H index very high in medical science, 68 on Google Scholar, and is made by this kind of publication. This is trend in research, is one of this predatory journal. So what is important here is that we are in the presence of what I call this kind of situation algocracy. Algocracy means that we are under the dictature of the numbers. In order to become good with H factor, with impact factor, and so on, we are constrained to have sometimes bad behavior. And there is a very interesting law which was made in the last century with respect to the ranking of the hospitals in UK, and the so-called Goodhart Saturn law that say when a measure becomes a target, it ceases to be a good measure. This is quite important, because this means that if you will have some good measure, you need to change the measure very fast, because the community is very good in order to accomplish the measure they are using in order to make a ranking of the people itself. So looking at what is the production of the results of this kind of empire of algocracy, you see that, for example, in the last year, an explosion of plagiarism. These are famous cases with physics in Turkey. There are 65 papers which are made by, was translated by Russian from article made in the 60s and published as new paper in 2000. Because you know that during the Cold War, the Russian published in the Russian language the journals. And the plagiarist cases are now on rise, and there are methods in order to control, and some journal made some controls, and they discovered that about 15% of the work contains some part which is duplicated. Sometimes it's not so important, but sometimes it's quite really important, because most of this work are perhaps not really interesting from the point of view of science, but they are papers which are used by people in order to have position, to make career. So this is an important point.
Stefano, you're close to your time. If you could maybe
okay, I go fast to the end. So you have you can see the different slides. There are a problem with the retraction. There are several cases of fraud in the last years, which means that these cases are growing. There are cases in chemistry, 2004, in physics, 2002, 2003. There are cases in physics in 2008, in chemistry, 2010, involving very important journals, Science, Journal of American Chemical Society, Nature, and so on. You have these important cases which is related to the vaccine. We are now in the pandemic. This is a very bad example, because this guy, Andrew Wakefield, succeeded in publishing some work on Lancet, a very important journal American, about the link between vaccine and autism is completely fake. But still, this is present in the web. This now no more in the medical register for UK, was expelled, but still the people are against vaccine for their children, because they say, oh, there was a paper published on Lancet regarding the link between autism and vaccine. So there are something which is also related to the fact that now we publish it with more and more with very beautiful picture. This is an example of my work. This is my first paper. This is drawing by the hand. It was in the 70s, more than 45 years ago. This is a paper I made some years ago. This is given by first principle calculation. But you see, this really very different how we present the results. And it's much more simple to do some publication of data with a new possibility that we have through digitalization. So I go rapidly to the end. And what happens here is that we are in presence of a change in science going from the KUDOS. KUDOS was an acronym chosen by Robert Merton, was a sociologist in the last century. And you write this KUDOS, which are the meaning of science. KUDOS means recognition. And if you look what is written here, he said that the reason of the success of science is that the scientists are able to follow these rules. And these rules at the end means recognition, and means the possibility to control really the affidability of the results. What happens now is we move to place. This is a very interesting book written by John Simon some years ago. And he proposed that now we move some KUDOS to place. Science now is proprietary, is local, is authoritarian, is commissioned, and you are no more scientists, you are experts. And place means position, no more recognition of simple position. So we think we have some problem with respect to the future, and I can give only some final idea. My idea is that we must, science is like life. We must have, we need more collaboration, less competition, more transparency, less hierarchy, more long-term knowledge and less short-term competencies. Knowledge are important, competencies are less important. We need more long-term jobs and less short-term contracts. We need more quality and less quantity. So what we can do is, for example, some lecture like this lecture, if we have in all the PhD courses, we have the possibility to have some courses related to research integrity skills, quite important. In order to have a position for the people, I think it's important that you need to have that the investigator that can also submit their doc papers, 5 or 10 papers. It's not important what you have made a lot of production. What is important is the quality of your production. So you need to submit 10 papers, the commission decide about the quality of your work in order. And also the grantee agencies must be prepared in order to give really money to the people. There are a set of publications which are really a good set of publications. So I can finish here. Thank you for your attention. And I have, I can now answer some questions.
Thank you, Stefano. I don't know what is the policy with online talks, if we have to upload or something, but you can assume you got your hands together. So Laura, if you can help me with if there are some questions. If not, I'm already ready to ask one myself, but of course I would like to give priority.
I don't know if anyone has any question. You can raise your hand virtually. If not, also Rosa may have questions. So.
Yeah, Rosa, go ahead, please.
Rosa, yeah.
Yeah, I had one question about the statistics of science that you gave. You mentioned one scientist per 250 inhabitants. How uniform is this worldwide? So where is the number of scientists higher and lower when we compare at least Asia, Europe, and the US, I guess, in Africa?
It's clear that this is related to the fact that we see an explosion of science in the last decades in China and in India. So the number is related to, if you see, for example, regarding the number of publications, 22% of the production is from US and 20% from China. And the same, more or less, is related to the number of scientists.
Okay.
And it is clear that the number of scientists here is related to scientists which are involved as scientists, not only in university and in research center, but also in industry. And what happens is the growth is quite large in industry now, because more and more, especially in US and in the northern country of Europe, industry are more and more hiring people with PhD. So that's the number is increasing. And what is not so much increasing is the number of scientists involved in directing research in university and in research center. This is quite important because it's something that we have now a growing number of PhD people. And I think that all PhD people, they think that his goal is to do some academic career, because also for us was this idea. And but we need to say to the people that this is really something that now is really difficult. I will say that less than 10% of the people they have a PhD and they continue to do some work in sciences could be hired in university and research center. The rest go to the industry or go to do other works. This is something important to know when some people start his PhD career.
Thank you. Very interesting.
This is also important. I mean, I and Riccardo, we are involved in theoretical physics. And one of the interesting points is that there was also an explosion of theoretical physics in the last years because of the development of computer center and big computer machine. But I think that now that we have really a number of people with PhD in computer science, which really too high with respect to the possibility to have position in university and in a research center. And this means that the people must know this point, because perhaps there are more possibility to be hired in computer center or in the industry, but not in order to do direct research, I will say uninterested research in this case.
So I know we are maybe a bit late, but I want, if there are no other questions, I want to ask you a very quick one, because I've met myself practically all the things you have been discussing in your presentation. Luckily, I never experienced myself the practice of coercive citation. So I've never been asked by a journal to add ad hoc citations. So I wanted to ask you, what is your feeling? How strong, how serious this problem is today?
I mean, it's serious for the journal which have very low impact factor. If you look at, there is some survey made by some group in the UK that for journal which are less than 1 in impact factor, there is a tendency to say to the authors, perhaps you can cite this work, which is published by the same journal, in order to improve. Because if you look at the journal with the impact factor, the majority of the journal are less than 1 in impact factor. And then there is journal, they go 2, 3, 5, 4, 6, and so on. And so this tendency. It's clear that something is also wrong with respect to impact factor, because impact factor work is made with respect to the number of citations of the journal. It's clear that it's different in the different topic. If you do, for example, medicine, so I will say that scientists in medicine with 70 H factor or 100 H factor is normal. For physics is so only 5, 6 pairs are about 100. So you need also to have really clear the different situation, the different field. But what I think is that really we need to be very fast in changing the measure of success. It's like in football. Now you see what happens with the goal made at home or the goal made in when you play abroad. You must change every few years the measure, otherwise this measure becomes very bad with respect to the effort.
Okay. Thank you, Stefano. If there is no last minute question, I
had one question, but it's very late, so we should move on. I only want to say to Stefano that it was very interesting, and it's very sad that this is so short because, I mean, this topic we can speak for hours. So thank you, really, it was amazing.
Okay. I can send to Ricardo the PDF of the presentation. Okay.
Okay, thank you so much.
Yes. Okay.
Amazing.
Thank you, Jonas. Bye bye.
So we join all of us acknowledging Stefano for his presentation, and now it's my turn to leave the word to Rosa, which is who is chairing the next session. Thank you, Stefano, and thank you all.
Bye bye.
Bye bye, and yeah, thank you. Because it's not that often that one gets that type of lectures. So now we come back to more technical topics, and I am happy to welcome Gemma Rius, who is a scientist at the Power Devices and System Group at the neighboring Institute of Microelectronics of Barcelona, which also belongs to CSIC, which is just on the other, in front of our building. And Gemma is now a scientist at CNM after a certain time as a researcher in Japan for several years as a postdoc, as an assistant professor, and now she's back here. And her research topics deal with nanofabrication. And so the title of her talk is Nanofabrication as Driver, an Object of Research. So Gemma, thanks for joining us today. And the screen is yours.
Thank you. Thank you very much. Let me start sharing my screen. So I think you may be able to see my screen now.
Yes, everything's fine.
Okay. In presentation mode, is it okay?
Yes. In presentation mode, better than this. Yes.
Perfect. Okay.
It was in presentation mode before.
Sorry.
Now.
Okay. Yes. No problem. Sorry about that. Okay, so good afternoon. Yeah, as it was mentioned, we moved to a more technical thing, and I would say that absolutely technical, because actually what I do is technology. So it's rather than science, or let's say, so it's technological or applied science. Right. So good afternoon, everyone. I would like to start thanking the organizers for inviting me to give this talk. And as the audience is quite broad, I just gathered a few basic ideas on what is nanofabrication and some of the tools and methods that are typically done. So this will be the outline of the presentation. So the first idea is, what is nanofabrication, right? Because actually in the context of nanotechnology, thinking about the concept of nanofabrication, it may depend a lot on what is your research, what is the development itself. So it's not the same to do nanofabrication for batteries, electrodes, than to do what I do, which is more related to nanoelectronics or integration of nano devices on electronics. So this is the idea, and it will also depend not only, let's say, in the applications, but also in the field, the viewpoint. So I'm going to give you more, let's say, the viewpoint of one who is related to microelectronics, which is, let's say, what I've been doing. And some of the issues are shared actually with other domains, but actually will focus on concepts like resolution and integration or compatibility about processing, because this is what it deals with. So from the microelectronics point of view, actually nanofabrication, it's rather, let's say, an evolutionary idea. So since the start of electronics and microelectronics and going to the integrated circuits domains, the idea is that when there is, as is shown in this trend known as the Moore's law, there was a linear trend on the increase of number of devices and along the years. And this was possible only because fabrication and microfabrication techniques and the processes involved on them and their combination was improved along the years. And this is what actually makes that our chips nowadays have millions of transistors, each one of them, and that we have within this miniaturization trend a high complexity and sophistication, which allows us to have our mobile phone as a complete computer, which is more powerful than sometimes our PCs in the, let's say, in our offices. So in that sense, all the things were miniaturizing, and especially transistor, the device, the basic device of integrated circuits was increasing in sizes. And actually, this was called the Moore's law, but there are further paradigms, let's say, in terms of technology, and you may hear about more Moore. So going beyond Moore, from the micro to the nano to the edge of this, or more than Moore, or beyond CMOS technologies for example, for electronics or for microelectronics and integrated circuits. And this is where things converge actually with nanotechnology. And actually, at some point in the 80s, there was this idea of new nanomaterials which have functionalities and properties very special because of their nano scale size, and also the possibility of accessing to their properties and to their characteristics because of some tool development such as SPMs or more in detail STM. So the idea here is that actually in that sense, the introduction of nanomaterials and at some point the limits of, in terms of thin films within the nanoelectronics, let's say, was a paradigm change because some of the devices and device concepts were different from what it was, let's say, previously known. And one example here is what I'm showing here, which is a single wall carbon nanotube field effect transistor, which is a kind of transistor, but which is instead of based on a channel which has a certain width and length, here it's a one-dimensional carbon nanotube, which let's say provides the channel to this device. So this is the paradigm change, and this has a lot of implications, and especially it has a lot of implications in terms of fabrication. And in this case, because it's a nanoscale object, it's nano fabrication, not in the sense of reducing the dimensions, but integrating new materials to give the same, let's say, functionality. So how do we reach that? How we can now, let's say, introduce those devices and address these applications in terms of, for instance, nanoelectronics, but let's say, can we apply the same methods, the same fabrication processes? And the answer is no in general for nanomaterials, but it's also no with the same materials, but to, let's say, to the limits of the resolution. And this is actually what happens in micro nanoelectronics, which is that at certain point, engineering and structuring the matter, or the matter that constitutes those devices and those integrated circuits into lower dimensions, and that we are reaching the tens of nanometers feature size. So needs of new concepts. So let's talk then on how we do that. And one of the things is nanolithography, or lithography techniques is the basic step where let's say, in sequences of processing, we build up all those integrated circuits. And the idea is that mainly, typically, let's say, optical lithography has been used. And actually the developments in terms of optical lithography, in terms of tool, in terms of light sources, and so on, allowed us to decrease the feature size, let's say, from the micron to the, let's say, resolution to submicron, which is in the visible range. But then further efforts were done to work on the ultraviolet and deep ultraviolet regime. But at some point, even if those techniques were implemented, there were two issues on that. One is that the wavelength also limits the minimum feature size due to diffraction, but also the cost increases quite a lot when we want to move to, for instance, extreme ultraviolet, let's say, photolithography equipment. And the other thing is that at some point, optical lithography, it's based on mask and a mask. So light is selectively exposed on the surface or the substrate through some mask, and the mask feature sizes have to be in this regime, in the nano regime. For instance, when we want to move to integrated circuits in the nodes, in the tens of nanometers node. And that means that the mask, the fabrication of the mask should also, let's say, be able to be done. And this is where, let's say, electron beam lithography plays a very important role. And actually, this was the first, let's say, application of, let's say, electron beam lithography, and it's still a very important one, which is actually, let's say, making the patterning for the mass fabrication. In that sense, let's say, in terms of lithography, electron beam lithography is not different from optical lithography in the sense that it selectively, let's say, irradiates a material which is typically a resist, let's say, relatively thin resist layer, which under exposure either becomes more soluble or more difficult to etch in some given developer, or a solution which is called a developer. And this is what we see here, that actually for instance, the irradiated part is this central one. If we have a positive tone resist, which is called a positive tone resist, we will have a hole under development in this green thin layer, which is the polymer that we use. Or otherwise, when we expose, we will have the negative tone resist, which resists better. So under upon development, it's the feature is defined. So these are, let's say, this concept is the same, but then there are essential divergences or differences from optical lithography or light exposure than electron beam lithography or exposure, which is the interaction. So and the nature of the light. So most commonly it started, let's say, the idea is that a very narrow electron beam of relatively high energy is delivered. And actually we are able to do that because we have very nice equipments which were developed actually for scanning electron microscope to focus in a very narrow spot size the beams. And here, instead of using a mask to do the local irradiation or exposure of the resist, what we do is to scan the beam in the area that we want to pattern. So this is essentially, it's very different. And let's say it kind of, let's say, this is the most common way. There are other, let's say, like projection and using mask and automatable masks, but essentially this is the main way of doing this. So scanning pixel by pixel the areas that we want to pattern. And again, because it's not light but electrons. The idea is that the interaction with the resist, it's different, but it's also different because it also interacts with the substrate. And this is actually the basis of the signal of an SEM, and is displayed here and has some implications on resolution and so on. So essentially here, the idea is that we are using electron beam because we overcome the diffraction limit, let's say, in terms of the wavelength of light. So, well, electron beam lithography in that sense is quite more, we can say that it's quite more complex than maybe optical lithography, because it depends, let's say, on how good is the tool and things like what is the filament type, field emission or thermal emission, which is the energy range that can be implemented with. The energy spread of will give you also more or less, let's say, resolution and the brightness, so the amount of current that it delivers will limit or not how fast you do the process. So these are some of the things, but the thing is that on the other hand, even if this is quite more intensive in terms of finding the conditions for the right exposure, the idea is that it's very flexible because, and this is the key point, electron beam lithography is probably most versatile tool that we have nowadays for nano patterning or for nano lithography. As it is used in a scan mode, one can have flexible designs. So in the mask is in optical lithography, we use mask, which is a kind of physical object, which is determined. But here we can change each time that we do the exposure, the patterning, we can change the design accordingly to what we want to test or obtain. So these are essential things. And the other thing is that also, thanks to digitalization of all those processes, all these things can be automatized. And then even if it's more, let's say the throughput is quite lower than optical lithography, which is a parallel technique. This is serial. So then in spite of that, let's say you can automatize all those actions and process at wafer scale, for instance, but also you can kind of align and combine with optical lithography for multi-layer, let's say, or for multi-level lithography, which very high precision in combination, for instance, with the interferometer stage. So yeah, this is what I was telling. It's a scan. So then the correct size, it depends on the implementation of the exposure, and this includes which is the resist sensitivity, how is the processing of that resist, but especially which are the correct doses, so which is the fluence and how the beam should be steered for having the better results and for reaching this ultimate resolution, which is about, let's say, in the nanometer, in the single digit nanometer scale resolution. So of course, every technique has some limitations. And as I mentioned, the main limitation from the, let's say, industrial point of view probably is the throughput. So we researchers are very happy because we can play around with the designs, but in terms of fabrication for mass production is maybe limiting. But another thing is actually that because of this interaction with the substrate, there are additional effects. We don't have diffraction effects that compromise the resolution, but we have what is so-called the proximity effect, which relates to the interaction volume within the resist and the substrate. But again, because we have digital, let's say, a steering of the beam, we can apply correction doses, as you see here with this changing, let's say, of the colors to represent the different doses, and they can be kind of adjusted pixel by pixel to give, let's say, the correct size. An additional thing, actually, in terms of limitations or, let's say, drawbacks of this technique is that actually, as I mentioned, the main application I'm doing is micro and nanoelectronics applications, and it is well known that microelectronics and integrated circuits are sensitive to charging, and especially charging at different, let's say, relatively high energies, because trapped charge can be in the barrier layers and delivered and trapped there and compromise the devices. And this is what actually here we have studied for a while, which is the effect of electron beam lithography on fabrication when we integrate let's say, nanoelectronic devices on CMOS, so in integrated circuits. So these are some of the things, yet I hope I have convinced you that EVL is a very useful technique and very versatile, and the advantage of let's say, having flexible device, especially for research applications or for prototyping, it's very powerful. But this is only, let's say, the nanolithography, so just patterning or just defining some features, nanometer scale features on this thin resist. But we cannot use it. This is useless at some point in terms of fabrication. So we have to think about not only nanolithography, but all the nanofabrication sequence. And that's actually some of the ideas. These are profiles, the sketch of what you do here is, here you pattern some thin film with, if you want, this applies also to microstructuring, but the idea is here to pattern, let's say, the resist with nanometer features, and then whatever you combine after this is what will give you finally some device or some functionality to that surface. And here we have a number of combinations. Essentially, we have additive or subtractive techniques. So this is the basics. We need, in general, what is applied in microtechnologies, micro nanotechnologies, is lithography step, which is followed by additive and subtractive techniques in order to find out, let's say, to end with the desired, let's say, architecture or device layout that we want. So here you see some examples. So once pattern adding colloidal, for instance, particles or nanoparticles, for instance, in this case. We can also use it for molding in different, let's say, ideas, or just using this opening, for instance, to edge the substrate and the underneath. And if you use multi-layer systems, then it kind of multiplies the possibilities of the different, let's say, structures that can be achieved. So this is this combination of nanolithography plus additive and subtractive techniques. But another thing is also to apply this the resolution at the nanoscale to let's say, to fabricate molds that will be replicated in another, let's say, in another way, let's say. So typically what can do is to do on silicon a mold and then apply techniques such as nanoimprint, which is kind of using, it's like a stamp. So using this on a thermoplastic, photothermal resist layer to transfer or the complementary, let's say, structure that you have in the mold. And this can be done in nanoimprint. I won't go to this further, but there is also sublithography, which is kind of similar, but in some cases simpler for, let's say, less resolution. And another idea also, if not, for doing nano patterning is the inkjet printing, which is a direct nano patterning technique, which simply is like let's say, printing, let's say, from inks, the desired features. And in this sense, this is very relevant for instance, for applications such as flexible electronics, which are not very, let's say, well addressed with other techniques such as electron beam lithography, for instance. And on the contrary, let's say, they have limitations in terms, for the moment, in terms of the feature size, the minimum feature size. So they are mostly applied to thin film, let's say nanometer thick thin film patterning.
Gemma, you have 2 minutes left.
Ah, okay. that's too fast. Okay, so I won't go to the details of the position of thin films, but I mean there are a number of techniques that can be combined with electron beam lithography, for instance, and to do all sorts of combinations. The thing is that on thin film, one of the ideas, and let's say the position, one of the ideas is the process compatibility, and a typical examples are, let's say, the integration of, for instance, new materials such as carbon nanotubes, or more recently graphene and other 2D materials, which actually are typically synthesized at high temperatures, and this is incompatible with essentially with any polymer that is used for nano patterning. So then different strategies need to be, let's say, implemented, such as, let's say, transfer techniques and so on, because they cannot be done on the final substrate, for instance. And this is adding, let's say, materials, but the idea is that we were talking about adding materials or removing materials, and that's another challenge, to combine the nanolithography techniques with nanoscale etching. And here again, I'm putting this example of graphene, which we, let's say, ideally would have, let's say, of both lateral and vertical resolution at the atom scale or molecular scale, in order, for instance, in the right side to do nanorivers, which have special properties in terms of nanoelectronics. And some of the ideas is actually using other kind of techniques combined with the nanolithography, which are the bottom-end techniques, such as block copolymers, which is self-assembly based on different kinds of materials, thin layers of polymers. So, well, going to pattern transfer and integration, the things get even more complicated, because it's not easy, and especially if you want to integrate those nano devices or nanoscale features on things like integrated circuits, then you need to kind of engineer your strategy. So these were kind of more, at some point, evolutionary, let's say, techniques in terms of fabrication. So lithography with additive and subtractive techniques, but there are two techniques which we won't have time to go through, but which I call the Swiss Army knife techniques, which are focused ion beam and tip-based methods. So in both cases, I will skip this, but in both cases, you can do all these three actions. So lithography, patterning, or let's say the nanolithography patterning, the addition or subtraction of material, you can do it with a single device. And well, one uses, instead of electron, let's say, or a focused electron beam, it uses an ion beam. And this has a lot of implications, because as I mentioned, you can directly, let's say, for instance, carve in the substrate. And the other one is tip-based methods, so nanolithography based methods, either on STM, let's say, equipment, or AFM equipment, which is one is a scanning tunneling microscope, or atomic force microscope. And here there is it multiplies the possibilities in terms of processing, because different implementations are used. They can be used in the case of the SPM techniques, they can be used in vacuum, they can be used in air, they can be used in liquid, and this combined with physical physical phenomena, both electrical and magnetic or whatever. So these are some of the varieties, and just some final words, which is that actually one of the main perspective or projection of nanofabrication is now in the quantum technology regime, because actually most of the solutions, for instance, in quantum computing and having qubits, is based on improving, let's say, the concepts and the devices, the performance of the devices that are based on, for instance, superconducting qubits or ion trap qubits and so on. And all this requires some development in the nanofabrication in terms of nanopatterning and also nanomaterials integration.
Thank you very much for the effort and
It was kind of speeding up
towards the end. And I apologize because everything is interesting, but the time is always limited. So we have time for one quick question. So please, I especially direct this to all the students. Don't be shy.
In case you think that you would be interested to apply your, let's say, to your research, you can contact me anytime if you want some, I don't know, discussion or assessment or whatever.
Okay, so they can contact you privately?
Sure.
Then just one question. You didn't mention at any point the cost of all those techniques. So to what extent the cost is going down for all of them with the economy of scale, or some of them will never be affordable? Or
Well, electron beam lithography already is quite kind of, I would say, affordable, because there are very kind of dedicated systems. Of course, it depends on what you want to process. So if you want to process, I don't know, 8 inches wafer scale and so on, you need a very special tool and quite a lot of know-how and so on. But there are, let's say, cheaper versions, such as, let's say, an SEM, which is equipped for electron beam lithography, just adding the proper software for beam steering and some beam blanker. So there are options on that to make it affordable. Of course, this thing of integrating the electron beam lithography based fabrication, for instance, it means sometimes things, and it depends on what you want to do. So, of course, if you want to pattern the whole wafer with nanoscale features, maybe it's not a good idea. So for this, nanoimprint was thought to be the solution, but still, let's say, the effectivity, if we are talking about nanoelectronics, for instance, for IC fabrication, the defectivity is quite an issue, and this is the same in block copolymers.
I think there is a question by Artur Romanov. So can you unmute?
Yes. Thanks, Gemma. I have a question regarding what do you think, who are nowadays the main drivers of innovation in this photolithography sector? Is it more the research or companies? Because I also know that there are big companies that deal with this, and can the academia actually compete with companies nowadays in terms of innovations?
I would say that, let's say, since long ago, the driver were industry, so the IC industry, of course, probably based on some kind of let's say help or whatever from the academy, but the investment was the industry, and let's say, actually, these are not so affordable, let's say, equipment. So deep UV and so on, it's really expensive. So you may need quite a lot of investment on that, and this is not the case for most of the universities. And yeah, definitely, let's say it's the industry, and will continue to be so. Actually, there is debate now on what to invest to, let's say, from now on, right, to make if it's the case, smaller nodes. So I think IBM recently released the 7 and 3 nanometer node, let's say, which is something that only, let's say, probably IBM does or Intel does and so on. So this is 3, 5, let's say, foundries around the world. So it's another, let's say, it's another league, let's say, at some point. Yeah. And we are, let's say, researchers, we are playing with other things. And yes, trying to, let's say, establish a few things more applied to, for instance, quantum technologies and so on. And then, yeah, in this sense, there is more, let's say, field for, let's say, for the academics to provide things which the industry maybe won't have the, let's say, the effort to be doing. No? So small, let's say, investigations or very basic investigations in order to improve, let's say, coherence times and noise and so on, until it's solved. No? So they will apply the solutions. They are working a lot, and they are very well positioned, especially when they can scale up, let's say, directly the fabrication.
And thank you very much, Gemma, for your talk and discussions. And I leave the floor to Xavier, who will introduce the next speaker.
Okay, good afternoon to everybody, and good morning to Susan. Susan Trollier-Markinski, you are around?
Yes, I'm here. I'm online.
Okay, thank you. Good morning for you. Okay, so it's a great pleasure for me to introduce the next plenary speaker, which is Professor Susan Trollier-Markinski. Susan is actually a member of our scientific advisory board of the Institute of Material Science of Severo Ochoa Action that we have in our institute. And so it's a big pleasure to have today the opportunity to listen to her with the talk concerning piezoelectric films for MEMS applications that you deliver now. Let me just summarize a little bit the long career of Susan in many different things. Susan is a professor of ceramic science and engineering in the Penn State in the US. He's professor of electrical engineering and director of the nanofabrication facility in the Penn State University. So her domain of research has been always around dielectrics, piezoelectrics, or ferroelectrics, mainly about thin films. And so she's following from the synthesis of the thin films, understanding the growth and the final applications and integration into devices, like you will see now. And so she has been recognized for many let's say, awards and positions around the world. I would just mention that she's member of the National Academy of Engineering, fellow of the American Ceramic Society, the IEEE, and the Materials Research Society, and also academician of the World Academy of Ceramics. At present, she's an associate editor of Applied Physics Letters. She was formerly the president of the Materials Research Society, that, as you know, is the largest materials society in the world. And she also served as president of the IEEE ultrasonics, ferroelectrics, and control devices, and so on. So I would just stop here because she has received a lot of different awards, and I would not mention all of them. But I am really very happy to have today the opportunity. And so thank you very much, Susan, for accepting our invitation. And please go ahead, and then we'll have some questions from the students for you. Thank you.
Thank you, Xavier, for such a kind introduction. Let me begin by saying that my primary job is as a teacher, and I am totally comfortable being interrupted as we go through. So it's much more useful, I think, if in a school situation, if you can ask questions as you have them. So please feel free. I won't be able to monitor the chat so well, so I will ask Laura if a question comes in on the chat. Please just go ahead and interrupt me, and we'll make this as interactive as possible. I know that it's getting later in the day for everyone there, and so sometimes it's easier to keep your attention if you can ask your question right away. So I will try and give a talk with the following outline. I'm going to say a little bit about what it is that contributes to the piezoelectric effect in thin films. And then I'm going to give you several specific examples where we can use either piezoelectricity or ferroelectricity to do interesting things in assembled devices. So here you can see us controlling motions of particles on surfaces. And so we'll talk about the piezoelectric micromachined ultrasound transducers for that application, amongst other applications. But I wanted to begin by first saying why materials are piezoelectric. And the easiest system to understand this is in the perovskite crystal structures. And I'm showing here animated the crystal structure of barium titanate as a function of temperature. So the green atoms that you see on the corners of the unit cell are barium, or in some cases lead atoms. The ones that I am showing as blue on the face centers of the unit cell, those are oxygen atoms. And the red atom that you see at the center of the unit cell is a titanium or a zirconium atom. And there's several important things to watch as you go through this animation. The first thing you see is that when the material is in the ferroelectric phase, this atom that should have been at the center of the unit cell displaces towards one or more of the adjacent oxygen atoms. And as it does so, we develop a spontaneous polarization. That is, if you average the position of all the atoms that sit on the corners of the unit cell, so 4 on the top of the unit cell, 4 on the bottom of the unit cell, the average of that position is right at the center of the unit cell. In much the same way, the average for the atom that's shown in red here is going to be wherever it displaces from the center of the unit cell, which means now that the center of positive charge is physically at a different location than the center of negative charge. This material has a spontaneous polarization. Moreover, as it develops this spontaneous polarization, you'll see that the entire unit cell changes shape. So associated with this spontaneous polarization is also a spontaneous strain. And in many of the perovskites, the spontaneous strain, you can see, will follow the direction of the spontaneous polarization. So here's just some slices out of that animation, where in the tetragonally distorted unit cell, this atom displaced in the up direction. It had 6 choices. It just wanted to displace towards one of the oxygens. So it could have moved up, down, forward, back, left, or right. Each of those was possible. And the spontaneous polarization direction is going to follow whichever direction that atom moves. And so does the spontaneous strain. So you'll see we now have a spontaneous polarization directed in the up direction, displaced in the same direction as that titanium atom. And the whole unit cell gets long, parallel to the polarization direction, and it contracts laterally. And so that tells you right away that there is a coupling between the electrical and mechanical energies. So I think I just saw a chat coming in. Let me see. Oh, you guys are not seeing the right slideshow. Let me get you the right one. Let's try that again. Sorry, everyone. Thank you, Panawit. I appreciate that very much. And does that look a little better for everyone? And I'll just move.
Better, thank you. I was active to interrupt you to tell you.
You are always welcome to interrupt me. So apparently I managed to share the wrong screen, so I apologize. I think you get the point though. So the material elongates parallel to the polarization direction, it contracts laterally. And because there's more than one possible direction for the polarization, we will have volumes of the material where the polarization is all going in the same direction. So in this chunk of the material, all those titanium atoms are displaced down towards this oxygen. In this chunk of the material, all of them are displaced off to the right towards this oxygen. So we're going to call those region domains, and we're going to count the boundaries between them domain walls. And which domains I can have and which domain walls I can have depend on the symmetry of the original material, as well as the loss of the symmetry element associated with the ferroelectric phase. So if I want to displace parallel to one of the original axes of the cube, there were only 6 possible directions I could have gone. And so I will end up with 90 or 180 degree domain walls. In the rhombohedrally distorted version, I displace that atom towards one of the corners in the cube. Well, there's 8 corners on any cube, so there's 8 possible polarization directions, and my allowed domain walls will be 71, 109, or 180 degree walls. And now we can start to think about, well, how does this material change as I apply an electric field? And so if I imagine some chunk of material that started, it was already polarized in the up direction, which means it was elongated in the up direction. And I now apply an electric field in the up direction, then what I do is tend to make that polarization bigger. So I'll take this atom and I'll drag it further and further off the center of the unit cell. And as it does so, the unit cell keeps getting longer in this direction and it contracts laterally. We call that change in the shape of the unit cell the intrinsic piezoelectric response. I can also get an intrinsic piezoelectric response if I change the distortion in the unit cell. So let's imagine now that this atom, instead of being displaced straight up, was displaced towards one of the corners of the cube. So the original polarization direction was at this angle. I apply an electric field at this angle. And in some materials, when the free energy function is relatively flat, I can rotate the polarization from this orientation to this orientation due to the applied electric field. And you can see that the entire material changed shape when I did that. So I can get polarization to rotate either a small amount or a large amount, and it will cause a change in shape, which is the second main contribution to the intrinsic piezoelectric response. Right. Cool. The extrinsic piezoelectric response occurs if I have domain walls, and those domain walls can move in response to the electric field. So let's imagine at time 0, we start with this material, where in this volume of the material, the polarization is all displaced to the left. In this volume of the material, the polarization is all displaced in the up direction. And so I have some materials that are elongated this way, another fraction of the material that's elongated this way. And if I apply an electric field in the up direction, I always favor the polarization which is parallel to the field. Remember, there's a term in the free energy function minus E dot P. And so I will then favor that orientation. And so that means that this domain wall is going to try to move so that I can make more and more of the up polarized state. And as we do so, you see that the material changes shape again. So this is what we call the extrinsic piezoelectric coefficient. And I've just reanimated those here, and I'm showing them grossly exaggerated to make them easier to see. But the key points to recognize is that the intrinsic piezoelectric response, which is just the change in the shape of the unit cell, and the extrinsic piezoelectric response in bulk piezoelectric lead zirconate titanate are about the same magnitude. So I get about as much of the net response from these two factors. That green line that you're seeing over here in the animation on the right is the domain wall. So as I move that domain wall, I move the spontaneous strain. But what this does not show at all fairly is that when I move domain walls, I don't get to move them through perfect materials. I always move domain walls through imperfect materials where there's some collection of defects in the solid. And anytime I try and move any plane through a defective solid, there's a finite chance that it's going to be hard to move that past that defect. And we call that process pinning. And so if I imagine a potential energy as a function of wall position, what that says is if the potential well is very, very deep, I can excite the domain wall kind of within the potential well. But if I remove the electric field, I'll go back to the same minimum. And so we would say we would have moved that domain wall reversibly. If, however, I can choose and move the domain wall from one well to the next, we have an irreversible contribution to the domain wall. And the challenge that's associated with that is that it increases the piezoelectric coefficient, but it also significantly increases the hysteresis, which means that it acts as a form of energy loss in the solid. And so we need to be very thoughtful about, for our given application, can I tolerate that energy loss or not? And there's some places where you simply can't tolerate it. And I show a good example of that here. So most of you are carrying around piezoelectric devices in your pocket, in your cell phone. So if you remember what a cell phone looked like a dozen years ago, it was very big, it was very chunky, it was very heavy, and it probably weighed a reasonable fraction of, a half a kilo. They were heavy. One of the reasons that they were so heavy is because in order to use this device, you need to have some way of protecting your receive electronics, which are very high sensitivity electronics, from your transmit electronics, which are really high power. And it would be very easy to blow up your receive electronics by transmitting on your phone, but that would make you unhappy. And so you need to figure out a way to separate out the transmit from the receive portion of the phone. And the way it used to be done was to take a dielectric resonator that was about half the size of my finger. It was made out of a very high density ceramic, and you needed one of those for every frequency band that you spoke on. Well, all of you appreciate that we're now in the 5G era, which means that there are many licensed frequency bands, and I need at least one of those filters for every frequency band. And that means if I still use that technology, we would have very, very heavy cell phones. And so about a dozen years ago, there was a major change where they replaced those dielectric resonators, heavy dielectric resonators, with tiny thin film bulk acoustic resonators. And this shows a dimension of a full duplexer solution. And just look at the difference in dimensions. It's about 1/4 millimeter high. It's about 1 millimeter on a side. You can afford to put 40 of those in a modern cell phone. And there are about 40 different filter devices in a modern cell phone. In that application, the key figure of merit is the electromechanical quality conversion, or the electromechanical coupling coefficient, KT squared. That says, if I put in a given amount of electrical energy, how much of that do I convert to mechanical energy? And the quality factor, which says, if I have this device and I start it resonating, how long will it keep resonating? So you have reasonably good working understanding of this. If you take a high quality bell and you strike a bell, that bell will continue to reverberate many times. It has a high mechanical quality factor. However, if I take my hands, which do not have a high mechanical quality factor, and I strike my hands, I get a simple single impulse of sound, and there's not much reverberation there. Okay, and so that would be a very low mechanical quality factor. And so let's just compare available piezoelectric materials. Here's aluminum nitride. It's got a kind of bad electromechanical coupling coefficient. It's only about 6% of the energy that I can convert back and forth. But this material has only intrinsic piezoelectric coefficients, which means that all of the energy loss associated with extrinsic coefficients is 0. Okay, which means we've got a pretty big KT squared Q. Other materials like lead zirconate titanate, which has that same perovskite crystal structure I just showed you, a much, much higher thickness coupling coefficient and terrible quality factor. And so there's just no competition at all in these devices. And so the cell phones, the filters that you use in your cell phones are either aluminum nitride or a scandium doped aluminum nitride. So that's where piezoelectric MEMS are currently important commercially. But there are a lot of other things that are potentially of interest, and I show examples of those here. So piezoelectric devices are ubiquitous in medical ultrasound. They're used in buzzers and beepers. We use them all the time as sensors and actuators. And many of those devices historically used bulk piezoelectric ceramics. So stop and think about everything you know from your ceramics classes. So I'm asking this question and I expect an answer from one of the people listening. What's a typical strain that you can generate in a ceramic without breaking it?
Come on, someone has to answer.
Say again, please and thank you.
No,
Someone has to answer. I won't go on until someone answers. So you must be students today. You must answer questions.
Because they are online, but they don't have to pass the exam.
Someone just take a guess. I don't care if the answer is wrong. Just guess. 1%? 10%? 100%? 0.1%? Rough numbers.
I would say maybe less than 1% or around 1%.
Less than 1%. Exactly right. About 0.1%. Beautifully done. Well done, Juan. So yes, roughly 0.1%. So let's think about something that I'm going to actually try to change its shape. So if I want to be able to have many millimeters of deflection, that means I need a really tall stack of device so that at 0.1% of that tall stack will generate useful motion. And so if you look at the devices that are used, for example, for diesel fuel injectors, they're multi-layer stack actuators and they're big, okay? But for the most part, those devices are also run at 100 volts. And it would be really, really nice if we could have much lower voltages and generate large deflections. And that, since we're typically limited about 0.1% strain, we just can't do just using the pure thickness mode of the device. And so we cheat. And the way we cheat is to take a material that is not piezoelectric and we put the piezoelectric on top in a sandwich structure. Now, when we apply an electric field in this direction, the piezoelectric's trying to get tall this way and it's trying to shrink this way. And it is stuck on something whose dimension is not changing. And so what will happen is that the entire material will flex like this. It will bend. And we use that bending motion to massively amplify the deflection we get out of the piezoelectric. And so the piezoelectric coefficient that describes that is the piezoelectric E31 coefficient. I'll call it E31F because it's kind of got mixed boundary conditions. So I apply an in-plane strain and I generate an out-of-plane polarization, or I apply an out-of-plane electric field and I generate an in-plane stress. And so I can make things bend. And so with a device like that, now with 1 micron of film, which I can actuate with 1 volt, I can get 1 micron of deflection. So more than 100% deflection out of the same device. So that's the coefficient I need. And when I want a sensor, I want a high E31 coefficient. If I want an actuator, I want a high E31 coefficient. I'm not going to talk so much about the piezoelectronic transistors. They're a weird bird. They actually use the outer plane coefficient. And for the energy harvesters, we need a high E31 times an H31 coefficient. And so for all of these applications, if I want to make a good sensor, actuator, or energy harvester, I need strong piezoelectric effects, which means I'm going to need materials like lead zirconate titanate for this application. And so let's have a couple looks at possible places that I could use those high strain piezoelectrics. So you see here, one of my students has a piezoelectric coated metal foil on his finger. Every time he moves his finger, he generates some energy. And so let's look at how efficiently we can do that. So if we were to think about that, we should recognize that most ambient mechanical energy is available below 120 hertz. Okay. And that means since we make micro electromechanical systems, usually the smaller you make something, the higher its resonant frequency. So now I have to take something that is inherently small and give it a low resonance frequency. Well, the way you do that is to make something very thin so that it will bend, and you hang a heavy weight from the end. And in that case, I can get a nice low resonance frequency. And if I imagine a cantilever-based energy harvester with a piezoelectric film on the cantilever, the power that I would get for that depends on the E31 coefficient squared divided by the relative permittivity, the volume of the piezoelectric, and the amount of strain I can generate on the piezoelectric squared. So I want a really high E31 coefficient divided by the relative permittivity. And so let's look at what we have. We have lead zirconate titanate 001 orientation. This is a fantastic piezoelectric. Has roughly an E31 coefficient of minus 10 coulombs per meter square, has a dielectric constant of around 1,000, which gives you a figure of merit for an energy harvester of 0.12 coulombs squared per meter to the fourth. Aluminum nitride is a fairly terrible piezoelectric. It's got a E31 coefficient of roughly -1, but it has a relative permittivity of 10. So this material is 10 times higher in piezoelectric coefficient and 100 times higher in dielectric constant. And so these two materials have the same figure of merit. And that made me very, very sad. And I thought we just needed to be able to do better than that. We needed to have a good piezoelectric and make it do good for us. And so the key to engineering that is to recognize that all piezoelectrics are inherently anisotropic, which means that the properties depend on the orientation. And if you look at a ferroelectric material and you put the polar axis out of the plane, that gives you the smallest dielectric constant. So the dielectric constant is actually bigger perpendicular to the polarization. And so I get a small dielectric constant, which I want, and the biggest piezoelectric coefficient if I can get all the polarization out of the plane. And so we calculated, if you could do that, we should go from this figure of merit of roughly 0.1 coulombs squared per meter to the fourth to about 1. It's a factor of 10 times more power out. That's worth chasing in many cases. And so we looked, could you actually build a material which put all the polarization out of the plane? And the answer is yes, you can. The way that you do that is to use compressive stress. So remember that we said that when you developed a polarization, the whole material got long parallel to the polarization direction and it contracted laterally. So if I squeeze the material laterally, I can push the polarization out of the plane. So all I need to do is get compressive stress. And so the way we did that in practice was to grow materials on substrates or fluoride substrates that had really high thermal expansion coefficients. And when you do that, sure enough, you get figures of merit about 1 coulomb squared per meter to the fourth. Great. Let's build a device out of that. And so we built this device. It had a brittle piezoelectric material, ceramic piezoelectric material on a ceramic substrate. We had to work super hard to pattern the substrate without ruining the ferroelectric. We developed an approach to do that. And now we have a thin layer out of all ceramic materials that we're going to hang a heavy weight on, and now we're going to shake it so that it'll serve as an energy harvester. Well, hallelujah, you take a thin material with a heavy weight on it and you shake it, and it's a brittle material, and you run a crack at the base of that, and you're done. Okay, it works great once, and then you're done. And so now you got to figure out, how am I going to take this nice idea and turn it into something practical? Well, what else has large thermal expansion coefficients and doesn't break when I stress it? Metals. And so we learned how to put passivation layers and orientation layers on metal foils. We use an atomic layer deposited hafnia as a barrier layer. Then we grow lanthanum nickel oxide as a orientation control layer. And then we can grow lead zirconate titanate on both sides of these metal foils. We lose some in the figure of merit for energy harvesting, but we don't lose everything. And these materials make great energy harvesters. And so what you're seeing here is a mechanical energy harvester. The piece that's bending there is a metal foil that has about 3 microns of lead zirconate titanate on both sides. And it's on a shaker table, which is why it's oscillating. And you can see that A, it doesn't break, so that's very nice. And B, we've used frame structures with 1, 2, 3 hinges that allow you to bow the entire structure into a pretty good approximation of a parabola. That is much better than a cantilever. And a cantilever, all of the strain is concentrated right near the root of the cantilever. And this is just along to control the frequency. It's pretty useless in terms of an energy harvesting perspective. So we kind of got past that scenario by bending the entire piezoelectric, and we could make nice low resonant frequency devices that are considerably better than anything else that's been made in the world. So you control the figure of merit, control the strain distribution, and you can make a pretty darn respectable energy harvester for the Internet of Things. We also looked at taking a very similar idea and building these into a wristwatch so that you could scavenge energy while walking. And you see an example of one of those here. So this is Chen Chen Shu's wrist. And you can see we have little piezoelectric coated beams. And every once in a while, as he rotates his wrist, an eccentric rotor, so that's a half ring with embedded magnets in it, swings due to the motion of the wrist. And as a magnet goes past the magnets on the end of one of these piezoelectric cantilevers, the cantilever oscillates, and we can pull energy out of the system when we do that. And you can actually generate usefully large amounts of energy. We were extrapolate that we could get about 140 microwatts when someone's walking. That's enough to power a personalized health monitor that's checking all the time your heart rate and the shape of your pulse. We're working now to be able to also be able to develop ones that will allow us to do things like detect air pollutants as well. So there's a good example of a piezoelectric used as an energy harvester. The next thing I want to talk about is using these piezoelectric films for actuators. And the application here is a little bit of a crazy one. It's for the proposed Lynx X-ray space telescope. So the current gold standard in X-ray space telescopes is the Chandra telescope. Chandra has 4 rings of paired mirrors. They're about 1 meter in diameter. They're about maybe about 1/2 to 1/5 of a meter in length. And the glass that they're made out of ranges from 1.5 centimeters to over 2.5 centimeters in thickness. Okay. And the reason they're so thick is the way you focus an X-ray is by reflection from a curved surface. And if you want to have something that is really precise at identifying objects that are at astronomical distances away, you need a really precise surface figure. And so that extremely thick glass was used just to keep it stiff enough that it wouldn't change its shape on launch. The problem is that glass in the Chandra telescope weighed 800 kilograms, excuse me. And it was so heavy that they could not afford the launch weight for the 5th ring that they had built, which means they only have 4 reflecting surfaces. You can only see relatively brighter X-ray objects. And so the Smithsonian Astrophysical Observatory came to us more than 10 years ago now and said, we would really like to be able to make the same idea, but we want to be able to make it out of 400 micron thick glass so that we can put thousands of these reflecting elements in the telescope. And we still need exactly the same surface figure. Well, if it's thin, sure enough, it will bend. And so now we need to correct all the distortions in the optical figure. And so they said, you cannot touch this side. This is where we're going to put our X-ray reflecting coating. You get the back of our substrate. Please put an actuator array on it. And by the way, we'd like a lot of it. So they're estimating they're going to need somewhere between 200 and 10,000 square meters of adjustable optic if they fly the Lynx telescope. And so that was kind of a fun problem. Okay, glass has a glass transition temperature. Stuff tends to deform above, say, depending on which glass you're using, 450 and 600 degrees C or so. So we had to learn how to drop all of our deposition conditions to much lower temperatures than we were working with. We did this by sputtering the films. We use stupidly long annealing times, and we literally do 0.5 micron at a time. We do that 3 times, and we can make 1.5 micron thick lead zirconate titanate layers on these glass substrates. And here you see the change in the surface that we are inducing by actuating 3 separate pixels. So we basically have 3 separate pixels. We're controlling the voltage on them. And as we do so, we're producing local deformations in the mirror figure. And that's what you're detecting, that the red color, we're actually locally deforming that. And the performance is stable, it's deterministic, it's good enough that it will match the half-arc second mirror budget that's been allocated for the proposed Lynx telescope. So here you see one of our mirrors in a flight-like mount. So this is the beauty side. That's the side where the X-rays reflect. And on the back, you see a whole bunch of piezoelectric cells, and you see cables that actually do the electrical interconnects for every single one of those cells to the edge of the cable. And now we have a device where we can actuate every single cell. So this is amazing. I'm so proud of my students. We did this in a university laboratory, and every single cell on that device operates. So extremely cool. You can see us actuating sequentially every single cell on that. And now we have a very large control problem. So let's imagine that each of our cells is going to be, say, 0.5 millimeter, or excuse me, 0.5 centimeter by 1 centimeter in size. And we want 200 square meters of adjustable optic. And I need a top contact and a bottom contact for every single one of those elements. That is a lot of wires. And so even if I have just a 40 by 40 array, that means I need 1,601 contacts. Okay, now scale that to the correct number of elements for the telescope. It's way too many to run that many interconnects. And so very thankfully, I have a colleague whose specialty is the electronics that are used in displays. And the electronics used in displays use a row column address scheme. And so if you could put a transistor on every single one of those cells, you can drop from 1,601 contacts for a 40 by 40 array to 81. Okay, that's a far more tractable number. All you need to do is to be able to put a transistor on every single one of those cells. And so we tried it. And we use zinc oxide as our thin film transistors. These are grown by atomic layer deposition. And what you can see is that you can build aside or on PZT capacitors, zinc oxide thin film transistors, and they work. And they work beautifully. And they don't change the PZT that's underneath it. And the zinc oxide doesn't care that it's sitting on PZT. And so you make these transistors with good source drain characteristics. We've getting electron mobilities on order 20 centimeters square per volt second. And we were able to achieve a functioning row column address on curved glass. And that took the scenario from where we had those super wide anisotropic conductive film connectors. We've doubled the number of cells on this particular mirror, and all the electrical interconnects come off on those wires. So that says you can make actuators, and you can make actuator arrays, and you can integrate them with all of the drive control electronics. The next thing I want to talk to you a little bit about is micromachined ultrasound transducers. And the idea here is fairly simple. If I want to launch a sound wave, I need something that's going to move, and I need something that's going to move out of plane. And so one way to do that is to take a passive elastic layer, put a piezoelectric on top of it, and actuate it. And now it's going to bend like a drum head. And I can control the frequency that that oscillates with based on the dimensions and the effective elastic constants of the material in question. And so we make these devices using a silicon on insulator process flow, where we start with a silicon on insulator wafer. We passivate the surfaces with SiO2. We grow a protection layer, in this case, hafnium oxide. We then sputter our bottom electrode. We start patterning. These devices we've done by sol gel deposition of 1 to 2 microns of lead zirconate titanate that's doped with niobium to control the conductivity. We etch to access the bottom electrode. So you've heard some of these steps in the last talk. So here we are using them at larger length scales she was working on, but we then pattern and sputtered our top electrode. We go through and we remove the handle wafer in desired regions. We dice into individual dies, and then we waterproof with parylene. And so that shows an example of a transducer array that replaces something like a device that would normally be this big by this big, would have a huge cable coming off the back of it. And we get not perfect, but reasonable performance out of these devices. And we've used them for imaging. This is the very first image we ever made. My student wasn't sure it was going to work, so he made a phantom target, and he made a heart out of clay and a broken heart. And he figured, maybe he'd be lucky and he'd be able to image. And you can see that, in fact, the first image, he imaged both the heart and the broken heart. So you can image. What else can you do with these? Well, there's very, very interesting work that's been done to control the assembly of particles in liquids above those acoustic elements. And I show here data from the literature that says that in most cases, the particles are going to collect in regions of high acoustic pressure. And you could use that, for example, to do blood sorting. So you can actually, based on the acoustic properties of the particles, separate them based on this acoustophoretic effect. And we said that sounded very interesting. It was done with a capacitive micromachined ultrasound transducer. Could we do it with a piezoelectric micromachined ultrasound transducer? And what we found based on modeling is that, in fact, it should be possible. And so we tried it. And so this shows an example where we have individual acoustic elements that we're changing which one's actuated and which one is not. And you can see that we have particles. These are about 4 micron silica beads in distilled water. And we could deterministically control where those devices went based on what was being actuated. This is, to our knowledge, the first example of acoustophoresis that allowed deterministic control without microfluidic flow. And so that is kind of an interesting thing. We can now imagine many potential uses for that. And then the final thing I'm going to show you takes a material that was originally intended for use as a piezoelectric, and now we're going to use it for a totally different application. We're actually going to use it as a memory device. And so let me talk about why this is interesting. So I show here a standard Moore's law plot. Transistors keep getting smaller and smaller. That curve may be rolling off in subsequent year, but we're still scaling fairly aggressively. What we have not scaled since about 2003 is the frequency of our devices. And that is not because we couldn't go faster. We choose not to go faster because in order to turn the device off so that the device does not draw a huge amount of current in the off state, we actually have not chosen to scale voltage. And you can see why that is if you look at the worldwide energy demand associated with computation. So the current estimates are that computing accounts for somewhere between 5 and 15% of worldwide energy consumption. The US data centers alone, 73 billion kilowatt hours in 2020. And this is anticipated to grow substantially over the course of this current decade. And so if we think about, well, what can we do to change the energy footprint of our computing needs? One of the things that we can do is to change the fundamental architecture of computing systems. So computing systems currently do all the processing on one or a couple of chips, and those are separated physically from the devices which serve as the memory, except for the very nearest layer of say, SRAM. So sometimes that'll be on the chip as well, but not always. And now the problem is that because if we look here, the density of interconnects between memory and logic is small, that means that I have to spend a lot of time and a lot of energy. The estimate is something like 80% of the energy in some computing systems is not associated with doing the computation. It's associated with getting the data back and forth between processors or back and forth between processors and memory. And so if you could vastly increase the interconnection between density and memory, we think you could vastly decrease the energy consumption. So that means we now need to be able to take our very high-end integrated circuit and build on the back end of it three-dimensional memory. And I said material that we're interested in here was originally a piezoelectric. Well, it's the same aluminum scandium nitride or the aluminum boron nitride that's now ubiquitous in thin film bulk acoustic resonators. But it turns out that if you add more scandium or more boron to that composition, it becomes a beautiful card-carrying ferroelectric. And this is just a fantastic piece of work that was done by the University of Kiel. This was Simon Fichtner's PhD thesis. I expect this is a PhD thesis that will be read for at least 50 years. I think all of us aspire to having someone wants to read our PhD theses after we write them. This is one that's going to be read. He demonstrated that this material has really very, very beautiful ferroelectric properties. And they're stable as a function of temperature. So here's data on aluminum scandium nitride, aluminum boron nitride, and aluminum nitride. We couldn't fully switch the aluminum nitride, but the other two switch stably over a really wide temperature range. They switch a lot of total polarization. The real challenge here is that their coercive fields are comparatively high, but the coercive fields drop, and they drop rapidly as temperature increases. One of the things that we absolutely need is to understand how these materials switch. And so we plotted the temperature dependence of the switching, and we looked at, is there an activation energy for it? And there surely is, but when you try to fit it with an intrinsic switching model, you get something like 4 to 5 orders of magnitude too small a coercive, an intrinsic coercive field. So that does not work. What we've demonstrated instead is that it looks like these materials switch by a domain nucleation and growth process. The activation energies associated with this motion. So these aren't really straight lines. I've just shown you 2 possible straight lines to show that this is something where there's some distribution of activation energies, but it's on order to 30 electron volts, which is really, really similar to the activation energy for domain walls in lead zirconate titanate. And so we're now working on trying to control that activation energy and control that coercive field and control the way these materials wake up when we apply electric fields. And so we're speculating that these materials reorient the polarization by moving domain walls. And if I stop at any one point here, what you can find is that there are crystallographic defects that I speculate move back and forth as this material switches. Those are the known defects associated with 180-degree domain walls in gallium nitride. And so I suspect that that's how these materials switch. I'll skip through this in the interest of time so that I can leave a little more time for questions. But what we're trying to do now is to basically develop new families of materials that do the same thing with smaller absolute voltages. And the zinc magnesium oxide looks like a fantastic candidate for this application. So with that, I will stop. What I've tried to show you is that you can use piezoelectric thin films to do some really quite fun things. If you understand the fundamental material science, you can do domain engineering that allows you to optimize materials for particular applications. We've been able to integrate electronics on these devices, make useful piezoelectric micromachined ultrasound transducers, and are now heading towards a close coupling of memory and logic in integrated circuits. So with that, I will thank you very much for your gracious attention and ask if anyone has any questions.
Okay, Susan, thank you very much for your nice presentation. As you said at the beginning, you have a strong educational profile, and we really appreciated these very nice films of how is the piezoelectric working and so on. So that's really very useful. Thank you very much. So please, if there are questions from the audience, I can see somewhere.
Artur has one question. Artur, you can speak.
Yes. Yeah, thanks, Susan, for the nice presentation. I have a question which is regarded page 17, where you showed the energy harvesting with piezoelectrics. Yeah, I think it's a clever technique to use a flexible metallic substrate in order to have the entire structure flexible for the piezoelectric. I mean, something similar is also used for superconducting tapes, coated conductors.
Absolutely. We borrowed substrates from that field because they actually give you the right orientation. So yay.
Exactly. I felt reminded of it. And now I have also a question. You said the thickness of the piezoelectric material is around 3 microns, I think, right? On each side.
So you want that to be as thick as possible, provided the material will be mechanically robust at the excitation. And so we found that as film thickness went up, you got more power out, but the strain limit at which crack propagation initiated dropped.
Got it. And how do you grow it? How do you deposit the piezoelectric material on the substrates?
So we've done this by 3 different methods at this point. We've done conventional sol gel spin-on. It gives you great films. One of the challenges there, though, is that the suction that holds the substrate in place puts permanent dimples in the metal foils. And so we've switched to either dip coating or to sputter coating.
Got it. Okay. Yeah, I think it's probably also very suitable for large scale coating then. Cool. Yeah. Thanks.
You're welcome.
More questions?
We have Khalid. Khalid, you can speak.
Hey, Susan, thank you so much for such a nice presentation. I have a question. Can you hear me?
Yes, beautifully.
Okay. The thing is that I have read that usually growing films on the piezoelectric materials, or especially the LSMO films on the piezoelectric material is like lithium niobate is a little bit difficult. So you have shown some piezoelectric material which have high coefficients of piezoelectricity.
Yes.
So, what about the growth of the different films? Is it easier on such kind of piezoelectric materials or not? Or like?
So that's a beautiful question. And the answer, I'm afraid, is always, it depends. There is no single good answer to your very good question. What we find is that it's very application dependent, what we can use as an electrode and what we need to use as the growth methodology. And so lanthanum nickel oxide and LSMO and even strontium ruthenate are comparatively higher resistivity materials than are pure metal conductors like platinum, which means they're great if you're going to use these devices at low frequency, and they're impossible if you're going to use them at high frequency. The RC time constants are devastating at high frequencies. And so for a low frequency device like an energy harvester, yeah, we use lanthanum nickel oxide all the time. One of the things that we're currently working very hard on is to try and increase the thickness of those layers and maintain high density. A lot of the chemical solution deposited materials are really prone to porosity when you grow them to the appropriate thicknesses. So that is something that we're constantly working on, is to try and make that good. For lithium niobate, the crystal structure is different. And so you're going to do much better on an electrode that will give you a close packed plane that corresponds to the oxygen-oxygen separation distance. And so that's more likely to be something like platinum 111 surfaces. LSMO, you'd actually have to probably go to a 111 orientation of the LSMO to template the lithium niobate well. That was a long answer. I'm not sure I totally answered your question though.
No, it's okay. I got it.
Okay.
Thank you. Thank you so much.
You're welcome.
More questions?
I have one question.
Yes.
It's me, Manuel Mas. Hello. When you were talking about the application on the telescope, yes. I don't remember exactly what the slide was, but what was the goal here? Because I didn't understand, because you want to have your thin film flexed, but I don't know if you really desire to have it complete, or have it. You really want to have. My question is, if you really want to have it the most flexible. My question was, which is the goal of,
Okay, it's actually, I should have explained that better. So the goal is to have an absolutely precise shape to that surface. Okay. The problem is it's thin and it's flexible and it's held to the mount at a limited number of places. And anything that's thin and held at a limited number of places is going to naturally bend a little bit. And the problem is that distorts the perfect hyperboloid shape of that. That's not a flat piece of glass. It's a conic section. And if there's any error at all on the conic section of the glass, it will degrade the focus.
Okay.
And so now the problem is I've got to correct that figure error by applying a voltage. And so the goal is to actually measure on the ground what's the real shape, determine the influence function for every pixel on the telescope, and then be able to, once it's launched in space and they've done the gravity release, correct for the gravity release, correct for epoxy errors and the fact that all epoxies drift over the lifetime of a telescope, correct for the fact that the mirror surface, the reflecting surface itself, its stress state isn't changing. So all of those things drift with time. But if they drift, they change the perfect shape of the conic section. My job is to fix it after the fact.
Okay, so you want a complete flexion.
We want to be able to bend each pixel by an amount that restores the telescope to perfect optical figure.
Okay.
So that may mean, say, this pixel here maybe would see 1 volt over the lifetime of the telescope. And maybe this pixel here will see 0 volts over the lifetime of the telescope. And this one needs 8 volts over the lifetime of the telescope.
Mm-hmm. Okay. Thank you so much.
You're welcome.
Can you tell how much you were deforming the mirrors? In which
We
range
get,
of?
so what we would like to be able to do is to have a total deflection amplitude on the order of 1 micron. And so we get that with about 10 volts applied for a 400 micron thick substrate. And so that's well within the lifetime limits for films of this type. So yeah, that's what we're currently doing. We're right now working on doubling the piezoelectric coefficient for the actuators themselves, so we can drop the voltage into or switch to silicon substrates, polished silicon.
Okay, thank you.
Yep.
More questions?
I think time to move on because we are a bit late.
Yeah,
So.
we should move. Okay, so thank you very much, Susan. It was really very instructive. We appreciate it a lot, and have a nice time in US.
All right, thank you. Everyone stay safe and healthy.
Thank you, Susan.
Okay.
Thank you.
Okay, bye-bye.
Bye.
So everyone, now we should continue. We should have a break, but we're a bit late. So we will have just a 5-minute break. We have Jillian already here. Hello, Jillian.
Hola.
Hola. Is it okay, Jillian, if we start in 5 minutes?
Of course.
Okay, so then, guys, you can take a little break and take a glass of water or something, and then in 5 minutes we are here.
Okay.
Right.
So welcome back, everybody. It is really a pleasure for me to virtually welcome Jillian Buriak. She's a professor of chemistry at the University of Alberta in Canada, and also a Canada Research Chair on Nanomaterials for Energy, Alberta Innovates Chair, Industry Chair on Sun Power Generation of Fuels and Power. And she does not only have a scientific life, she has also dedicated a lot of work to editorial activities, first in science, then she moved to ACS Journal. She was editor-in-chief of Chemistry of Materials for quite some time, and I'm glad to have the opportunity to interact with her at that time, which was absolutely a pleasure. And she's now associate editor for ACS Nano and editor-in-chief for ACS Materials Letters. So she has had many awards. The ACS Nano Lectureship Award, she's fellow of the Royal Society of Canada and of the American Association for the Advancement of Science, amongst others. So Jillian, thanks so much for accepting our invitation, and yeah, the screen is yours.
Wow, well, thank you so much, everybody. Thank you, and thank you, Rosa, it was wonderful. It was a great pleasure for me to finally meet Rosa. We had worked together for so long, and unfortunately, we're obviously not meeting together right now, but it's looking good to meet together soon. So thank you so much, everybody. Can everyone see this? That's kind of the standard question these days, right? Can everyone see my screen?
Perfect.
Oh, thank you. So I'm going to tell you a little bit about some of our work on block copolymer self-assembly, which when you're getting old like me, you can say you've been working on for a really long time. And so I just want to thank the people who did the work. And so you're going to see a lot of work by Chong Jin, who actually defended his PhD in 2017. And just to give hope to the graduate students, even when you graduate, people are still going to continue working on those results that you accumulated as a graduate student. And so what I'm going to be finishing with is his work, which we literally just published. So there is always hope for your good results. So Chong Jin, as you can tell, he's a very strong person. I also want to thank Eric Luber, who's an engineering physicist in the group, and he does Cirque du Soleil. So he's way above the ground. And I'm saying, Eric, please take care of your head here, because, that's where the engineering physics takes place. I also want to thank Brian Olson. So he actually has 2 more biological experiments, which I haven't shown here. And he's a coder statistician, and you'll see his work, his hand throughout. And Gayashani Ginagay, so she actually comes from Sri Lanka, where she was on her university basketball team. And so she's a graduate student athlete. So we had an introduction from the previous talk talking a bit about Moore's law, where we started. And so oh my goodness, 15 years ago, a little more than that, we were very interested in using block copolymers to do the hard work for lithography and patterning on computer chips, because lithography is the single most expensive cost factor in computer chip manufacturing. And at the time, there was something called the ITRS, which was the Industry Technology Roadmap for Semiconductors. It's now called the IRDS, the International Roadmap for Devices and Systems. You can look this up online free of charge. It's actually now on the IEEE website. And it's a really neat thing, because industry leaders from the 5 geographic producing or areas of the world that produce the majority of the world's semiconductor chips, they send representatives, these are academics and industry people, to get together every 3 years to contribute to the new version of the roadmap. And in the roadmap, you can find a section called directed self-assembly. And the language that they use is this quote of, it's an innovative technology. And now the word innovative is completely overused. Everyone's like, I'm so innovative, you're so innovative. But really what this means is a very specific term, meaning we as industry people think that your technology, I'm not an industry person, but the industry people say your technology could perhaps be commercialized and scaled up, but there's a lot of work that still needs to be done, but we think that there is promise. That's basically how you would summarize that. And so in the IRDS roadmap, they say that this idea of directed self-assembly is an innovative technology to solve nano patterning challenges, because the idea is that you use the molecules and the polymers that contain the chemical information to know what to do to undergo self-assembly, to do your lithography in a much more cost-effective manner. So you're having the molecules do the hard work. And so just a kind of very, very high level overview of what that means is that you take a diblock copolymer, and that's where you have a polymer that has chemical composition of one. So of one side here represented by A, that's covalently holding hands with a different polymer of chemical composition B. And of course, as chemists, you can make these, and luckily for us, because we're inorganic materials people, we can buy them from polymer source. And so you can change the ratio of the molecular weight of A to B, you can change the composition of A to B. And so luckily the macromolecular people have done so much beautiful hard work, and they've come up with what are essentially phase diagrams. And so you can look these up. Again, we're inorganic materials people, like, this is great. It's kind of like a cookbook of, I'd like to make this today. And so you can look up, you could say, so would I like these cubic, body-centered cubic dot patterns, or would I like these hexagonal cylindrical patterns, or these amazing gyroidal patterns, lamellar, and then the inverse. So I can go to these phase diagrams, and they're all published, and I can say, I'd love to make this lamellar structure. And so you can go in there, and that will then tell you what the molecular weight of A needs to be with respect to B for this particular chemical composition. So it's great. So the idea is that we're taking a bowl of noodles, and those noodles contain the chemical information necessary to undergo nanoscale phase segregation and form these complicated patterns. We don't need to do anything. They do the hard work. And that's why the lithography aspect would become less expensive, because we don't need to do that. The molecules do it. And so you can see how this could be of interest. And so BCPs, that generally is the lingo for, or the abbreviation for block copolymers. And so just 3 very simple examples. Block copolymers have different molecular weights. And so if you could then, instead of making the bulk 3-dimensional structures, you confine them into something called a monolayer, which is on average about 30 to 40 nanometers thick. It's going to be dependent on the actual block copolymer you choose. You need to figure out what that thickness is that would correspond to a monolayer. But if you choose one block copolymer that can form these hexagonal dots, you could then use this as an etch stop, for instance, to carry out anisotropic etching, and then you can etch into the underlying semiconductor or whatever material you're interested in to form a high fidelity pattern that mimics that of the parent block copolymer template. Cylinders, the lamellar structure. And of course, this is a bottom-up process. The resolution could be as low as 5 nanometers. You're really bumping up against entropic considerations when you're getting that small, but people are looking at that. Large scale patterning, because here's a very crude overview. You take a bucket of your block copolymer, you mix it up, and you literally pour it on your surface. Of course, it's going to be a little harder than that, because it's these slight variations in thicknesses will play a large role, but that's kind of the idea. And it could potentially be low cost. And so the industry that has really taken this and hit the ground running, of course, which makes sense, is the hard drive bit pattern media industry. So the idea is that you take block copolymers and that they could actually make these or assemble these magnetic bits. And so that's why Seagate and IBM and others have been pushing this quite hard. So when we first got into this, we were very interested in making line structures. So we're going back, and so this is a block of polymer made of polystyrene block poly 2-vinyl pyridine. We've converted this into platinum. I'll show you how we do that in just a second. It's actually very simple chemistry. But with this block of polymer, we have we're doing the self-assembly on a very large flat surface. So this is actually a piece of silicon. And so it's kind of like if you have, here in North America, we have these things called demolition derbies where people drive their cars all over the place. There are no roads, no curbs, so that would be undirected. And so in this case, you have short-term or short-range order. The center spacing of these lines is about 36 nanometers in this case, but there's no long-range order. You get these fingerprint patterns. And so let me just quickly tell you how we convert these into metal, and you can convert these patterns into basically any metal that you want. And so here again, we're making the monolayer of the polystyrene block poly 2-vinyl pyridine block copolymer. And the cylinders that are embedded within the monolayer are composed of poly 2-vinyl pyridine within polystyrene. If we then dip this into a dilute acid HCl, 1 molar, 1% HCl or HF, depending on what you want to work with, is that these protons find little defects in the polystyrene and protonate the poly-2-vinyl pyridine. That poly-2-vinyl pyridine then becomes really charged. It becomes poly-2-vinyl pyridinium, basically a polymer salt. All this charge causes a massive volume expansion, probably about 10-fold volume expansion. And so it can only go one direction, and that's up. And so then the poly-2-vinyl pyridine block, which is our chemical handle, which was embedded in polystyrene, it was unreachable to us, now becomes completely accessible. We can then just soak this into an aqueous solution of an anionic metal salt. And you want it to be anionic, so it could be PtCl42-, AuCl3-, whatever, it doesn't matter as long as it's anionic. It then undergoes ion exchange with the Cl- or F-. You then load it up and a 30-second simple plasma clean, and it reduces the metal ions to metal 0. It removes all your block of polymer. It's amazingly high fidelity. I'm still amazed 15 years later that this works the way it does, because I would have expected the metal to go splat, but no, it actually follows the block of polymer template. And so you can form these structures. And so here in this case, instead of it just being kind of crazy, the block of polymer can self-assemble in any way it wants, is we provided a little bit of direction to the block of polymer. So here on this piece of silicon, we've etched into the surface a trench that's 30 nanometers deep and about 600 or 700 nanometers wide. And so the block of polymer, if we put on just enough that actually fills the trench, it will undergo long-range self-assembly that follows the walls of these trenches to give you that long-range order. So you don't have the fingerprint pattern, because this is actually the equilibrium structure of the self-assembly. Here we've got a triangular pattern, again, 30 nanometers deep. The block of polymer is in there, and it decides to self-assemble off of one side of the triangle. Down here in the bottom left, you can see there's a circular trench. In this case, the trench is sufficiently perfect that the dog catches its tail, and so you end up with this concentric ring array. In the bottom right, you see that there's actually a very slight defect. And this was a defect in the actual pattern that we were using. We were doing E-beam lithography to make these. And so instead of forming concentric rings, you actually have this yin-yang. You have two separate wires. Again, we've converted all these to platinum through the method I just mentioned before. But and so you have two separate wires, and you get the yin-yang kind of in the middle. So I'm going to show you a different block of polymer that we're going to be working with a lot here today, just in the next 20 minutes. This one is called polystyrene polydimethylsiloxane. So it's called PS-PDMS. And in this case, one of the blocks that contains a silicone, so that's the PDMS part. And the silicone gives us the silicon, the elemental silicon that will then, when we do that plasma treatment, simply converts that block into silica. Okay, so you can end up with dots. We don't need to load it with metal ions. It just automatically forms that because it contains a silicon. And so in this case, here's the fast Fourier transform. This is a 3-micron scale bar. This is a very large two-dimensional crystal. And I say very large because in the block copolymer field, anything that's more than a few microns in size, a single crystal, is considered quite large. Because what happens on a surface is that you have isolated nucleation events. And they're completely isolated in the sense that nucleation over here doesn't know what's going on with respect to nucleation over there. And so these two-dimensional crystals grow, and then they impinge on each other. And then there are these weird defects, like, whoa, it's kind of like you look at maps of older areas of Europe, you have these villages that grew, and then where they meet, the streets don't line up. It's exactly the case here. And so, so this is a very large, perfect single two-dimensional crystal. Now you say, okay, well, for block copolymer lithography, this looks kind of easy now. You have a block of polymer that forms these nice patterns. You can use these morphological features on the surface to get long-range alignment, but there's a big problem. And the problem is when the polymers get small, you run up against entropy. And so if you have polystyrene PDMS, that's the block of polymer I showed you just in the previous slide, this center-to-center spacing of this block of polymer is 24 nanometers. So you can see that here, it looks pretty. But if I choose a block of polymer that is smaller, and this is again published by Seagate, so a hard drive manufacturing company, this one is smaller, the molecular weight, the center to center spacing is 12 nanometers, but you can say, whoa, the image on the right doesn't look very ordered. It looks messy. And so what's happening is that the segregation force, the chemical difference between these two blocks is not sufficient when the molecular weight gets small to induce that order. And so you have people who are working on making block copolymers that have two blocks that are very chemically different. So this is the work of Mark Hillmeyer, Grant Wilson, for instance, at the University of Texas, Austin, to try to make them different. So this is part of the challenge of why we haven't seen this applied in industry yet. So what we were interested in doing was, can we hack this? Okay, can we play tricks with this? And I must admit, we found this by accident. So if you take a block of polymer that forms cylinders on a surface, and instead of making it thick enough to form a monolayer, you, by accident, form a bilayer, that second cylinder, it's kind of like when you had two toilet paper rolls lying sideways. The next layer up is going to sit in the interstitial space between the two ones on the bottom. And so when we do that platinum, we load it up with the platinum anionic salt like I showed you, and then do the plasma treatment. The cylinder that's up top, when we go and remove the dimensionality here from basically 3 dimensions to 2, it falls between the 2 and the bottom. And so instead of just having the spacing, the natural spacing L, the intrinsic spacing of this block of polymer, you actually get L over 2. So you can actually decrease the spacing by a factor of 2 through this hack. Okay, so this is hacking. So you can choose a block of polymer that gives you very nice ordered arrays. And by doing this hack of doubling the density or doubling the thickness of the films, is that you can decrease that by a factor of 2. And it actually kind of works with a caveat. It's not perfect. So here we have the single lines, and then you have the double lines underneath here. So we're choosing this 100 nanometer scale bar. It's the same in both cases. Now you can see that the spacing of here from the bright lines is about, in this case, just under 50 nanometers. And in the doubled lined image in the bottom left-hand side, you can see that you see this motif of bright, dim, bright, dim. And the tilted SEM over in the top right gives you a sense of what's happening. So where I draw here, the bright lines those are derived from the cylinders that were at the bottom of this bilayer. And the dimmer one, those are the lines that are derived from the cylinder that was up top. And the reason why it goes bright, dim, this is actually an artifact of imaging by SEM, because what's happening is that the lines on the bottom are actually tall and skinny. And the lines that were derived from the layer or the cylinder that was higher up are fatter and wider. And so this is just so imaging by SEM, the taller, sharper images give you the brighter lines just because of the way the secondary electrons are scattered. So you have tall, short, basically. It also works with the dots. So it's not perfect because the lines that are derived from the top cylinders are not exactly the same as the bottom ones. But maybe as a proof of principle, it gives you nice images and kind of proves a point that perhaps there's something there. So in this case, we've actually shown that if we provide some features on the surface, in this case, we've drawn the bright lines here using graphoepitaxy, using e-beam lithography. So these are silica lines. And then when we spin coat the block of polymer on there, it's about 40 nanometers thick. We platinize it. Platinize the block of polymer. We end up with that bright, dim motif again. And over in the right, you can see this is a large circle that we've drawn. Again, that bright, dim morphology. So the tall platinum lines, the short and fat, the tall, the short and fat. And so it's not perfect. The lines derived from the top cylinders are not exactly the same as the bottom, but as a proof of principle, okay. But it still wasn't perfect. And so Chong Jin, so that's the guy, that's the weightlifter guy. So he said, okay, what if we then take our block of polymer dots, for instance, the polystyrene polydimethylsiloxane block of polymer, and do a 3-step approach. So we're actually going to separate this into 3 steps. Now I know anyone who works in industry would say, oh my goodness, you're going to go and do 3 separate approaches or 3 separate steps. So you're adding complexity. Totally get it. Again, this is just fundamental science. Spin coat the polystyrene polydimethylsiloxane onto a surface. We then do that plasma etching. We convert them into silica dots. Put another layer of the block of polymer on there. And at the time, we had no idea. Would the second block of polymer layer feel the underlying features that we had produced via the first plasma etching step? Would it align? Would it be commensurate? Would it try to organize itself with respect to those silica dots? If it does, it would form a honeycomb pattern, and then we can do yet another step and make this triple density pattern. Okay, at the time, we didn't know. So this actually does work. So here up top is the cartoon image, the first layer. You can see the silica dots, 200 nanometer scale bar, a slightly tilted SEM image. The second layer represented by green, it does align itself with the underlying block of polymer, the dots produced by the block of polymer, giving you a honeycomb pattern. And then a third layer represented by yellow does align itself into these interstitial spaces. So you do form a triple density pattern, but there are imperfections, and these dots wiggle a bit, and we do a lot of statistics in that paper if you're at all interested. But here's where it got kind of curious, and this is where the last part of what I'm going to talk about today. What if the polymers don't match? And so this is when you have a graduate student who just tries something completely different, and at the time I would have said, this is just going to make a mess, and it doesn't. So Chong put down a given block of polymer that formed a first layer of dots. He then chose a second block of polymer that doesn't have the same spacing. And so we wondered, after he had told me, he said, what do you think this is going to do? And I said, well, maybe the top block of polymer will change its spacing because it's a polymer. It's flexible. What does it care? It could change its spacing to fit itself to align with the underlying block of polymer and etch it. But that's exactly what it does not do. So what he found when he did scanning electron microscopy or helium ion microscopy is he saw these triangles and flowers everywhere, like triangles. What the heck is that? So you look at the scanning electron microscopy image and say, Moirae superlattices. So Brian, so he's the one with the three kids I showed you in the beginning. He then took the scanning electron microscopy images and wrote code that would allow you to separate the top block of polymer pattern from the bottom one. And what you can see is that the block of polymers actually have different spacings. So the second block of polymer, the top one, it does not change its natural equilibrium spacing or periodicity. I thought it would just have squished itself to fit the bottom one, but it doesn't. It says, nope, this is my natural spacing and I'm going to adopt it. But in order to reduce the energy of the system, it actually decides to rotate a very small amount. And this is what's called the angle of offset in order to reduce the overall energy of the system. So instead of changing its spacing, it just adopts this angle of rotation. Here in this case is 3 degrees. And being able to separate the bottom and the top patterns allows you to determine that angle of offset. And so so what do you do when you're in this case and you say, that looks cool, but I have no idea what it's good for? Sometimes you have to just kind of go with it. And so Chong, what he did is he went into the lab and said, okay, what spacing polymers do I have? I have 23 nanometer spacing and I've got a 34. So I'm going to put down the 23 first and then the 34 nanometer. And using Brian's code, we can actually then separate the bottom layer, the top layer, and determine that angle of offset. And so for this particular combination, it adopts a 30-degree angle. But we didn't know why. We had no idea. We had no predictive value or ability at all at this time. He then did the reverse, 34 and 23. Bottom is bigger spacing, top is smaller. It adopts an angle of offset 11 degrees. And then 43 and 34, in that case, it's 3 degrees. Like, oh, okay. So what you can see in some cases is that you can, again, form these very large two-dimensional crystals. This is the fast Fourier transform. This one, instead of forming a triangular pattern, is what we kind of call the flower pattern. And so you can see up close. But what we saw is that over large areas, as is the case with block of polymers, is that you have those individual nucleation events on a surface, but they are completely isolated. They're not in communication with each other. And so you have these crystals forming, and then where they meet, you have these domains or these boundaries where there are a lot of defects. Now, when people publish papers in this area, they will, of course, we all do this. We always kind of crop the images so all those nasty boundaries are outside. It's always good to put those in the supplementary materials because a lot of interesting stuff happens here. This is a very, very large scale image taken with a helium ion microscope. So if you have access to a helium ion microscope, it's really cool because it gives you very high resolution over a very large area. And so using Brian's code, he was then able to color code these images based on the angle of offset. And these are actually chiral domains because -30 is the opposite of +30. And so you can look at this and you can see that these purple areas are in fact the areas of where the nucleation events, those islands, meet at the grain boundaries. So it's hard to tell from this, but you actually form majority phases. So the block of polymer, when it's doing self-assembly, it actually tries, it's not like it's human, I'm anthropomorphizing the polymers. It actually does form a majority phase of one particular angle of offset. Now, I didn't convince anyone that it's forming majority phases. It just kind of looks like a mess. Now, Chongjin wasn't convinced either. And we wanted statistically relevant data that we could use for machine learning. And so what he decided to do was, this is actually animated, this little cover, is could he make 2,800 templates by electron beam lithography and then allow us to generate statistically relevant information that would allow us to understand what's going on and provide predictive value. And so with electron beam lithography, instead of doing block copolymer assembly for that first hexagonal array, is cool because you can, on the same chip, you can change the spacing from say 10 nanometers to 12 nanometers to 14, all the way up as big as you want. And so that would then allow you to then systematically investigate the changing of size. So he does an e-beam lithography array of silica posts instead of doing block copolymer assembly, puts the block copolymer on that, does the self-assembly, and then we etch it. And so we did this is a 5 micron scale bar. These are circular arrays of the dots. A close-up shows you these are the silica dots done by e-beam lithography, not block copolymer. Put the block copolymer on there and you see the Moiré superstructures. Okay. So this is just a subset of 35, just to show you that you get beautiful patterns in every single case, but they're all different. And so that is using the algorithms and the applications that Brian had written allows you to generate a lot of statistically relevant data. So we're not going to go into this. But what Brian saw in these images, and he came to me, he said, I'm seeing these swirly patterns all the time. And you're like, swirly patterns? That's weird. And they're chiral and they're kind of grouped together. So you can see the green ones in one direction and the pink ones in the other direction. And you could really see it when he color coded it, showing the lattice rotation. Kind of looks like, a Van Gogh type of thing. And so what we figured out what was going on is that, and this took a long time, this is why Chongjin, he graduated in 2017 and why we only recently published this paper, is that we had no idea what was happening. And then we found, this is where sometimes it's great when there's a delay. In the physics literature, people are working on these two-dimensional van der Waals epitaxy type structures. And people noticed something that had been predicted back in the early 70s called static distortion waves. And what this is the system is trying to further lower its energy and it undergoes these funny distortions. And so these were predicted again in the mid 70s, but they were first observed only in 2016 in a completely different system. And so this is Fritz and co-workers in Germany. They were looking at the self-assembly of these beautiful little molecules on graphite. And I'm just going to show you the table of contents image because it shows it very nicely. Is that what they found when these molecules self-assemble onto graphene, which itself has its own very strict periodicity, is that the system, when these molecules self-assemble, there are very slight distortions in the molecules in order to further lower the energy of these two-dimensional crystals on the graphene. And so represented here, you can see these swirly patterns. And what this is representing is the distortion in the actual carbon-carbon bonds of these coronine molecules. And now they've represented them multiplied by 15, a factor of 15, because they're so small. So this was only seen because of amazingly precise and careful scanning tunneling microscopy. but it enabled us to say, oh my goodness, that's what's going on, static distortion waves. And so this has turned out to be really interesting, is that you're seeing that in twisted bilayer graphene, for instance, is that it's generating ferromagnetism, superconductivity. This has turned out to be this amazingly fascinating and rich area of physics that we by accident stumbled into. And so we're using these as models for understanding some of the energetics of these twisted bilayer structures. And so Brian saw that these static distortion waves, these funny little twists, seem to be grouped together. And so the last thing we're going to show you is just this model. And so when you don't really know what's going on because you have a complex system, you have these hard silica dots on a surface. You've got this block of polymer self-assembled soup, basically, under plasticized conditions. You allow the self-assembly to take place. And so how do you analyze that in situ? Pretty difficult. So Brian used the LAMPS open source software to do a molecular dynamics simulation. And so underneath here, which you will see emerging in this simulation, are the hard dots that represent either the silica dots we've made by block copolymer self-assembly or by e-beam lithography. So he used what's called a nose Hoover thermostat. So we have the block copolymer that we've modeled here that is being heated to form this homogeneous melt. And there you see the circle of the silica dots that's emerging. So we're going to increase the speed here, otherwise this takes a long time. So the top block of polymer, the epi layer, so it's frustrated. Now it's trying to lower the overall energy of the system. It's frustrated because of that energy, because of that periodic mismatch. And so what you see out of this is that those static distortion waves represented in green emerge, and pink here. And so the system is, not only does it adopt that angle of rotation to lower the overall energy of the system, but it also adopts this funny little twist, these mass or static distortion waves, to further lower the energy of the system. And you can see down here, this is a little histogram in the bottom right-hand corner. You can see that it's bimodal. And so the reason why this is of any interest is that when you are, for instance, making an organic device, like an organic electronics device, and you're putting one layer on top of another, organic photovoltaics, organic field effect transistors, and these are crystalline, is that how these are aligning with each other, the crystalline, whether they match or do not match, can lead to interesting structures at these interfaces. So I'm hoping that I've shown you that polymer noodles can allow access to a wide variety of different patterns, and that you're not limited to the equilibrium structures that they give you. You can actually fiddle with them. You can actually hack them. And so one thing that we found just by accident is that if you are doing epitaxy in this case, and you're working with soft materials, is that they can have an extra little twist, or they can do funny little things in order to lower the energy of the system. And so static distortion waves are turning out to be something of great interest for a number of different fields. So I just want, oh no, I don't have my acknowledgement slide. Where did it go? Darn it. Let me just go back to the beginning again to thank the people who did this. So Chongjin, Eric, Brian, and Guy Shani. And I'd like to thank you so much for inviting me to talk today, and I'd be happy to answer any questions.
Thank you so much, Jillian, for this magnificent talk. It's really interesting. So I presume there are questions from the students. Don't be shy.
Please don't be shy. You can always email me too, if that's of interest.
Well, maybe I will break the ice. Arthur, yeah.
Hey, Jillian, thanks for the really nice talk. You said in the beginning that, unless I'm mistaken, that this technology is potentially cheap technology, right? So what does it make it still expensive, or how can you still decrease the price of the technology, or did I misunderstand something? Is it already very cheap? Because it seems kind of simple.
Absolutely. Okay, so the best, if you want to learn more about this, follow up with Grant Wilson. So read the work of Grant Wilson and Paul Neely, because Grant works very closely with Intel. So he's at University of Texas, Austin. So he can explain this better. While it looks great on paper, you need to, what is the defect rate in existing silicon-based technologies? So, we're all carrying, it's hard to see with the zoom. There we go. We're all carrying these around. Okay. And so if you're going to be making 1 billion chips or 1 billion transistors on a chip, your defectivity is essentially 0. And so much of the issue of the block copolymer self-assembly is that the defectivity is quite high. So about 5 years ago, the semiconductor industry, through the International Technology Roadmap for Semiconductors, told us, the academics who are working on this, your defectivity rate is, or your level of defectivity is too high, about 5 orders of magnitude too high. And so that's why the sparse patterning of putting onto the surface these features that will then nudge the block copolymers to form the right structures with the right orientation is needed. And so it looked like the field was undergoing some real challenges, because the field decided, or the field shifted towards extreme UV as carrying out some of the 6 and 5 nanometer lithography. But work again by Grant Wilson and Paul Neely and others have really kind of brought it back to the forefront by carrying out this, by integrating this sparse patterning to enable the block copolymer to be nudged into the right direction. But so it's actually still a very ripe area of research. There's still a lot of work to be done. And so it's not a question of cost per se, it's a question of getting the block copolymers to do the right thing every time. I know I just rambled, but
no, it's I think explained a lot for me.
Because there's so many things going on. And I like a lot of us, we kind of thought, oh, the field isn't doing so well, like 5 years ago. So since Intel and others went towards extreme UV, but it's undergone this renaissance over the past couple of years through a few kind of interesting discoveries related to the sparse patterning that people do. So it's interesting. Things are evolving.
Yeah, there is another question, please. Yes.
Hi, Jillian. Thank you for your talk. It's like very interesting, and I love your energy with the presentation.
Oh, thanks.
I just have a question. Like, what would happen if you grow like a linear polymer on top of a dot pattern?
Oh yeah. So love that. So people have done this. Sang-Uk Kim's group in Korea, for instance, and it's tricky. So the linear structures have a little more, I'd almost just call it very loosely, I would never write this in a paper, more of a tensile force. And so you do get some alignment, and then they decide to change direction. So it hasn't been investigated anywhere near as much as the dot pattern, because the dot pattern has a clear line towards making bit pattern media in terms of applications. But the line patterns are very interesting. And so, but they do tend to bend and decide, oh, I'm going to change direction. So if you want another person to look at is Carolyn Ross. So do follow up with her. So she's at MIT. And I'm actually talking to her group tomorrow. So they have linear type arrangements on dot structures that they've made via e-beam lithography. And they form some amazingly complicated and beautiful patterns. So that's a good starting place. Good question.
No questions? No. Yeah, I do have one. Actually, I wanted to ask about the homogeneity and the defects, which you said it was a problem. So does the work on machine learning and so on, using the thousands of templates you have prepared, help to that respect? Or is there something more to learn before being able to design or to have some predictive ability?
So just to even keep it really simple. So we have a paper that just came out in ACS, I think it's still in ASAP. It's ACS Applied Materials and Interfaces. This is Guy Shani's work, where she's applying machine learning to simply making just flat layers of single monolayers or just single layers of block copolymer dots. Really simple. No double patterning, no moire structures, just simple flat structures. And so how you do the annealing process for that, whether you're doing solvent annealing or thermal annealing and things like this, can have very large, can play a large role in the defect, the level of defects of these block copolymers, or even just for simple flat structures. And so she applied machine learning type approaches to optimizing that. And so the idea is that if someone says, okay, I've got this block of polymer, it has the right spacing, how do I even over a very large area, let's say I have a 13-inch wafer, what's the best way to get the lowest defectivity structures for that? And so so she applied machine learning to that. And it's a very simple question, but it's actually still very hard because there's so much entropy. You're really fighting these mushy molecules that want to just do their own thing. So
yeah, it's really interesting. And it's nice that the students have the opportunity to see that not everything can be designed, that in many fields, one has still to learn from I wouldn't say trial and error, but the machine learning or serendipity or that. It's really, really nice.
Yeah, and you can apply these machine learning design of experiments type approaches to sparse data. So this is something, if let's say you've worked 2 years and you say, I've got this great system, but I have to defend my PhD in 6 months. I don't have a lot of time. How do I then go and make it and convert this into a device or a structure? And so, do have a look. So the design of experiments allows you to quickly scan parameter space, scan multiple variables simultaneously, without needing that much data, and allows you to find the right direction faster.
Yeah, it's really interesting. So is there any other question from the students or no? Well, you have one?
Jillian, where's the photo? The photo that you have in the back.
Oh yeah, I took that last weekend. So that's in Jasper National Park. So yeah, that's about 3 hour drive, a little more than that, 3.5 hour drive due west of here. So I'm actually facing west. So unfortunately, we're just far enough you can't see the mountains because here it's very flat. And then all of a sudden the land starts to roll a bit and then whoop, Rocky Mountains. So
it looks really nice.
Come visit.
I will. I hope so.
Okay.
Well, yeah, thank you very much, Jillian, for all your energy.
Gracias, and everyone, stay safe and healthy.
Thank you. And thanks to all the students. It was a hard day, but I think it was really worth it. So see you tomorrow.
Bye.
Bye. See you tomorrow. Then at 11:30, we have the welcome activities. So I hope you like them. We have prepared nice activities for you. If you have any questions regarding the organization, now is the time. If not, see you tomorrow, 11:30, okay? I hope you like today's session, and see you tomorrow. Bye.
Thank you. Bye.